Magari se mi metto in piedi forse. Andiamo così. Dici quando parte. Okay. Good morning everyone. Our people connected. We know that we are, there were 100 people registered, so for all of you, welcome to this webinar. I'm Professor Leonardo Marchese. I will coordinate the webinar, this half-day workshop dedicated to functional organic, inorganic, hybrid, and catalytic processes. This webinar is dedicated, at the end of a long story, more four-year story on a European project of Horizon 2020, dedicated to developing catalysts, hybrid catalysts for multi-site reactions. And we decided to conclude our project dedicating few conferences as to disseminate the main results of the project. But we also wanted to invite two distinguished scientists in the field, Silvia Bordiga, Professor Bordiga, and Professor Hermenegildo Garcia, to deliver two lectures on some, let's say, hot topics in this field. So welcome to Silvia and Herme. Herme, I didn't see you still connected, but you will join us later. So just let me introduce a little bit the program and the project. But before doing that, if this works, okay, let me say where we are at the moment. We are in the Villa San Remigio on Lago Maggiore in Verbania. This is a residence, this villa is a residence of the University of Piemonte Orientale, which is dedicated, which is used for summer schools and conferences and so on. We strongly wanted to conclude this project and the subsequent conference in this place, inviting all of you, but unfortunately, the pandemic still keeps some limits on this, on the movement, on the transport and so on. But I really wanted to have a part of the group that worked on this project in my department, which is involved in this project. So some of the people are in the audience, so I welcome all of you. Thank you for coming. We will have an enjoyable time, I'm sure, both on science and let's say enjoyable time together. So concerning the project, let me say, sorry. Concerning the consortium of this project is related to eight participants, 8 partners of 6 European countries, namely C6 and Almiral is a pharmaceutical company, a Spanish pharmaceutical company. So C6 from Spain, CNRS from France, Solvay in Belgium, University of Southampton, UK, two partners from Italy, University of Piedmont Orientale, where we are, and Cage Chemicals, a small company based in Novara. And at the end, and not for the importance, for the relevance, P&O in Germany. So, as I said, the project was based on the development of catalysts, multifunctional catalysts, which will be able to catalyze complex reaction to produce pharmaceutical compounds or let's say pharmaceutical active components and specialty chemicals. The peculiar things, the peculiar science in this project is that we wanted to develop systems, catalysts that are able to make in a single reactor, in one pot reactor, we might say, a reaction, a complex reaction which needs to have several steps, 2 or more steps, all in the same pot, in the same reactor. So what we call the tandem reaction or cascade reaction sometimes. So we developed several catalysts. I don't want to enter too much in details. Some results, main results, will be delivered by partners. But you might just to summarize the efforts that we did. We prepared more than 200 catalysts to reach some really relevant results that we discussed yesterday with in a final meeting, technical meeting with the officer and a reviewer. So we were very happy of these results. But more than that, we are very happy to collaborate in this consortium. Now, for going rapidly to the webinar, to the workshop, as I anticipated, Professor Silvia Bordiga will deliver, is one of the two key speakers, plenary lecture, we might say. He'll deliver a lecture on spotlight on zeolite and metal organic framework catalyst, similarities and differences, strengths and weakness. But before giving the words to Silvia, Professor Bordiga is a really, first of all, is a friend. Let me say, Silvia is a very good friend of mine. We studied together, we started together science, so I'm very linked to her. We worked at the Department of Chemistry in the University of Torino, where she's still there as a full professor in physical chemistry. And among all his interests, he's also a professor in Oslo, University of Oslo, where she spends several weeks or sometimes months per year. So her interests are on, let's say, developing methods for characterization, especially in situ characterization or operando methodology. She's very expert on that and a variety of techniques, and that she will give us some examples. But I like to mention that she coordinated, she won an ERC synergy grant based on copper-based catalyst on carbon hydrogen, on the activation of carbon hydrogen bond. So it's a quite let's say hard topic. So you might mention something about that, I suppose. Well, just to conclude, she's really eminent scientist, demonstrated by well, around 460 papers. He has an ACA index of 100, 100 today 103, but is rapidly growing, and around 40,000 citations. So he's one of the cited scientists in Italy, even at the international level. So, Silvia, the floor is yours. So you have 30 minutes. If you spare a few minutes, we can keep.
Listen, it's written that I cannot share the screen. I need to receive the permission, it seems. Okay. Do you see my screen? Hello? Do you see the screen?
Yes, yes.
Yes, Silvia, it's good. Thank you.
Okay.
No problem.
Thank you so much. So thank you very much for this nice invitation and for the nice words, Leo. So I want to start with a light, in some way, light talk, choosing a subject which is in the close vicinity of the topic that was developed in your project. Talking about materials which are microporous materials, and first of all, they are crystalline. So in principle, we have the possibility to know the building block that is supposed to be constant in the lattice, with the peculiarity of having some changes maybe at the surface. And I've chosen this picture from Asia, which is describing nicely how the surface can change the property of the material. And in case of microporous, where we have a large extension of porosity inside the crystal size, we have some trouble sometimes, defects, but sometimes those defects can be the active site. And so we are interested and in order to know the activity of them. So starting from zeolites, the building block is the simple tetrahedron, and through the link of the oxygen, we have the possibility to make different networks. And the properties are related to porosity, which are in the range of 0.31 nanometers. So normally we consider these molecular sieves. And so big molecules cannot enter inside the pores of these materials. And we have the shape selectivity. And sometimes we need to change the dimension of the pores with some treatment. And I think that this was part of the work that was developed in your project. Then we have the possibility to change the composition, and so adding the chemistry to the lattice properties. And we have many structures. And at the moment, we have more than 200 known zeolite structure, and some of them are also known in nature. Here I've taken some of the structure from the atlas of zeolites. And as you can see, we have a structure with porous with shape of channels, or cages where we can have a larger space inside. So the possibility is to have the mobility of molecules inside the channels, especially if the channels are interconnected, which is not the case of this zeolite, which has just straight channels as reported in the picture. I said we have the possibility to play with the framework, but also to the chemistry. And so by replacing some silicon with for instance, aluminum, we obtain materials which have, for instance, acidity if the counter ion is the proton. And in this area, we have a large variety of application of zeolites, for instance, in the area of the petrochemistry. And the big change in this field came when it's been introduced the use of the templating in order to enlarge the possibility of structures and also of composition, because zeolites with a high aluminum content very often don't need a structural directing agent, but when we want to prepare materials with a lower aluminum content, instead, very often we need this extra element, which guide the building of the three-dimensional network. The peculiarity of these materials having at the beginning, after the synthesis, an hybrid structure, because we have the organic inside the channels and the inorganic part, which is making the lattice, is that upon calcination, in air, we can remove completely the organic part and reach the end with the porosity of the material. And this is a big point in favor of these materials, for which we can easily obtain porosity in the lattice. And I will show that in case of MOF, this is not always the case. Coming to few examples, I want to recall some study made in collaboration with Enrica and Leo to characterize the acidity of these materials, zeolites and zeotype. In this case, is reported the effect of the interaction of ammonia on a SAPO34. And here we have studied in detail all the possibilities interaction of ammonia forming ammonium ion that in the different structure of the zeolite were able to reach a local structure which was different, changing in the symmetry of the ammonium site depending on the local structure of the cavity. Another possibility is to develop zeolites where we have a substitution of heteroatoms. And in the past, in Turin, but not only in Turin, also in this case, we had some work together with the friends in Alessandria, the study of TS1. In this study, for instance, is reported the effect on the lattice change, introducing titanium inside the lattice of the silicalite in the MFI network. In particular, by introducing the titanium, we observe a tension inside the lattice, which is not isotropic, and the effect is different in the different cell parameter. And this is an important information because testify that the titanium is inserted inside the lattice, and also is telling us that it's not possible to introduce a huge amount of titanium inside the lattice. Conversely, it has been proved that the active titanium, on the contrary, is just a titanium which is isolated inside the lattice of the zeolite. The final area that I want to mention is related to zeolites where the catalysis is played by the counterion. And in this area, a big relevance reached the zeolites exchanged with copper. In particular, copper chabazite is one of the material used for practical application for the composition of NOx using ammonia as a reducing agent. And by choosing the proper composition in terms of aluminum content and copper exchange, it has been possible to develop catalyst active starting from quite low temperature. In particular, starting from 200 degrees, it has been shown that the catalyst is active. And in respect to this system, quite recently, the group of Paolucci, and then also we were able also to add some pieces on this story, discovered that copper in presence of ammonia is forming a molecular unit reported, the sketch is reported in the picture. And this species is a sort of homogeneous complex encaged inside the zeolite. And so in some way we have something between an homogeneous catalyst, because we have the structure which has a molecular structure property inserted in an heterogeneous catalyst. And so in some way this is a nice example where the concept of heterogeneous catalyst is approaching the concept of the homogeneous catalyst, which has a very specific molecular definition. So this was in some way the introduction for the zeolite sector. I want now to tell something about the metal-organic framework. This word was coined in 1999 in respect to the synthesis of MOF5. And this material was the start of a new era in the development of materials constituted by organic linkers with some rigidity, like the building block reported here, in combination to some cations, metal cations. This was not the start of the era of coordination polymers or structure solids with crystalline structure, taking into account the combination of cations and organic linkers. But till to that point, we had a large variety of metal complexes, coordination compound, but with the lack of the idea of having materials which were able to keep porosity in the lattice. And so in the same year, we had the appearance of two milestones, so the synthesis of MOF5 and of HCAST1. And from this, a huge amount of material were made. So if we go to the rigorous definition of metal-organic framework and we compare this with the coordination compound, we have that for metal-organic framework we should have these three characteristics. So we have to extend in 2 or 3 dimensions the property of a crystalline structure. The materials contain organic linkers and contains potential voids. And this is, at least on paper, a peculiarity of these materials. If we compare zeolites and MOF, zeolites are, we can say, well-known materials. They have large-scale applications as molecular sieves and industrial catalysts. And we have a new direction in synthetic treatments and the synthesis of hierarchical systems. And these materials have, in general, surface area in the range of 100 square meters per gram. And so they reach at maximum, anyway, the surface area is always below 1000 square meters per gram. Conversely, in respect to metal-organic framework, we can say that we have an exponential growth in the number of materials and potential applications. However, at the moment, we have just niche application of this material for very specific application, and not a big process are performed using this class of material. And we have sometimes some conflict in the interpretation of the results, and sometimes we have a nice drawing of materials with the description of a local site inside these materials, but not always we have strong evidence about this structure, because we have materials which are extremely complex, and so we should be careful in looking at also the literature data in this field. In general, however, as the component, so the major component of these materials are organic, because we have the organic clinker, we have a surface area which is in general higher, an order of magnitude higher in respect to the zeolite class of materials. So in 1 gram of MOF, we have more than one field for soccer, and so it is amazing the space that we have in principle available to run, for instance, reaction. So if we compare the building block of zeolites and metal organic framework, in the case of zeolites, we have the possibility just to play with the angles between the different tetrahedra, and so we have a limited amount of possibilities. Conversely, in case of MOF, we can play with the different arrangement of the surrounding cation, playing with the specific coordination connection of the different cation used, and the huge variety of the organic linker, which can have different connection in respect to the cation. And so we can have linker with for instance, an arrangement like this one, or with linker with arrangement like this one. And so we can end with a huge variety of structure. So at the end, the structure can have cations which have a fulfilled coordination sphere, or a structure when even we have cations where we have a coordination vacancy, and so where we can have already some chemistry at the node. Then we can open the possibility to make in a precise way system with defects, removing selectivity, some linkers, and so starting to play with the chemistry of the lattice. However, one important point at the end of the synthesis is to be able to remove the solvent. And this is not an easy task. This is a nice example where, in case for a MOF related to the zirconium with the zirconium cluster, is moving from the sample as made, which is reported with the black curve, moving upon the activation, so trying to remove the solvent. We observe that already at room temperature, a large portion of the solvent is removed. And activating at mild temperature at 300 degrees, we are able to remove all the solvent, so water, and also DMF, which is used for the synthesis. And so we are able to obtain an empty material where we can play with the chemistry. However, this is not always the case. In the case of, for instance, this material, we were able to obtain a TGA with a nice plateau, as reported here, but this is not always the case. For instance, for this material, instead, we obtain a much more complex TGA profile, and also the evolution of the infrared spectra show us that in this case, we don't have just one family of OH group as expected at the node of the zirconium cluster, but we have more than one site. And so for sure, in this case, we have a material with some distribution of defects, most probably lack of the linker inside the lattice. As I told you, the importance of removal the solvent, and sometimes after the solvent removal, what we obtain is a material with a large porosity, but then we have to be careful about the stability of the material. In fact, most of these materials are not stable in presence of moisture. and they are destroyed, so they lose crystallinity when they are in contact with water or just the moisture of the atmosphere. So some of them cannot find broad application for this problem. For instance, UiO66, if it's made in a proper way, it is able to resist also the contact with moisture, but this is not always the case. In particular, if we think about the stability in respect of chemicals, the unit, the MOF constituted with the building block with the carboxylate moiety are more stable in acidic environment, while the MOF with the linker containing the nitrogen are more stable in basic environment. And so we need to pay attention when we decide how to use the material. Another important issue in respect to these materials refers to the mechanical stability. Very often, upon, for instance, pelletization process, the MOF are losing the crystallinity. So in this case, for instance, a MOF, the UiO67, is not able to keep a pressure after 2 ton. And in fact, if we compare the XRD pattern of the powders, we observe that by increasing the pressure, we really decrease the crystallinity. And so starting from 2 ton, we lose the crystallinity, and so the MOF is totally gone. In principle, we can play with the synthesis, changing the linkers, and so using mixed linkers. In this case, for instance, we have a comparison of different materials with the same fundamental building unit, so the decarboxylic acid, but in some cases, in one case, we have substituted the linker functionalized with the amino group or with the nitrose group or bromine. And then we can use the spectroscopies, in this case the infrared spectroscopy, to underline the presence of the different group. We can make these materials having all the linker functionalized with the extra atoms, or for instance, we can play having mixed linkers. And in this respect, we can follow, for instance, some fingerprint of the material, in this case, for instance, the NH vibration, and we observe the possibility to monitor the level of exchange of the linker by monitoring, for instance, the increase of the vibrational property of the NH, which are substituting in the linker, as reported here. I like this picture taken from a paper from Seth Cohen, where we have reproduced a knife which is used when we go picnicking or trekking, and this is a full set of tools available to do some specific chemistry, for instance. So the idea is to modify the material, changing some building block in order to obtain some specific chemistry. And this has been attempted in many ways. And this is an example where different approaches has been used. So for instance, one post-synthesis where all the ingredients were put together, or by using a pre-made linker with already the functionalized platinum inside the linker, or a post-synthesis treatment where we start with the mixed linker with the BP presence inside, and then we include the presence of the platinum after the synthesis of the MOF. it has been described the possibility to exchange the linker also in a quite defined way, moving to the protection, exchange, insertion, or polymerization of different linker inside. And so on paper, we have a huge variety of possibilities, but sometimes the synthesis protocol and also the possibility to characterize in detail the material is quite difficult. And so these are very nice drawings, but sometimes it's very difficult to control in practice the appropriate procedure to obtain the wished material. So just to conclude, I've shown some example where we can play with zeolites and metal organic framework, guiding the formation of local defects, introducing ligands that at the end can insert also a specific species, for instance, in this case, a platinum ion. And then these materials can be modified also to include, for instance, metal particles, and playing with the synergy effect of having the cages of the moth in combination with the metal particles. And just to conclude, so my feeling is that still for zeolites and moths, we still have a long way to go. Both materials offer large opportunities in the development of new heterogeneous catalysts. Despite the similarities in the synthetic approach and characterization tool, each of them have specific peculiarities, and the disclosure of complex behavior requires the combined use of complementary technique. And in order to develop the knowledge in this, I suggest to use a series of material and not just to work on one sample, because very often those are so complex that we really need to follow trend in order to understand our materials. And with this, I want to acknowledge and thanks for the attention, all of you.
Okay. Thank you, Silvia. Okay. Thank you, Silvia, for your very interesting talk and delivered by as usual in a very effective way. If someone wants to ask some questions or give some comments, they can write on a YouTube. People that are connected from in YouTube, but people in the audience, let's say in the virtual room, can ask directly to Silvia some question. Robert, Urbano, you have some comments or questions? Robert?
Well, just a comment to say, as usual, Silvia, good to see you. And thank you for a really engaging presentation. So you really covered in this very short time, you know, the advances in zeolites and the emerging prospects with moths. So just a curiosity, and probably you've been asked this question many times. So, you know, with the emergence of moths, there was so much excitement about being able to capitalize really on the idea of having these mixed metal nodes with the organic linkers to impart functionality, right? So I think one of the main prospects we saw then was changing the hydrophilicity and the hydrophobicity with the use of the moths, for example. So with the zeolites, we had traditional petrochemical applications, refining applications. And with the moth, you have these more emerging applications like gas, hydrogen storage, gas capture. So would you just share with us some brief prospects on where this is going to go? I mean, we already know that moths are very good for hydrogen storage and carbon capture. Where do you see this going in the future?
So for sure, the area of separation and gas separation is a sort of more mature area for these materials. Concerning the catalysis, in respect to gas phase catalysis, I have some doubt, because it's very tricky to be able to keep the availability of the site, the local structure of the site, having most of the volume empty. Conversely, in respect to liquid phase catalysis, maybe this is could work better, but then it is very difficult to evaluate also what I find in literature. Very often, too nice drawings, which are just drawings, but then it's very hard to push back, especially when this is coming from very big names. Maybe the chemistry is exactly what is claimed. I'm not put in doubt, but the description of what is reported too often is not true, cannot be done on the basis of the results available, because it's extremely complex, and too often signals are too mixed, and so the progress is low. While as all the system is pushing to bring results, and this is not good, especially for the new generation, because sometimes when the young are starting, so the first suggestion that very often our generation is giving, go to the literature and try to reproduce what has been done. That on paper seems very simple, and then it sort out that it is a disaster, and so the frustration starts to rise. And so this is my feeling. So for instance, in the project, in the ERC project, we are trying to develop hybrid materials for the CH activation. So one of the reaction, not the only one, but one of the reaction is the direct conversion of methane into methanol. And for instance, what is reported for this reaction on MOF is not good for the moment. So I don't know where we will go, but for the moment is still dark, very dark.
No, thank you for your frank answer. As usual, you've been very forthright. That's really good. Thank you.
Just to complete the discussion between Robert and Silvia, what about the cost? No, because all silica-based catalysts or silico-aluminate catalysts are very mature. We know them well. We can prepare well. There are challenges because you have two students preparing the same catalyst, and sometimes you don't have the same result. So it seems simple on the paper, but then when you prepare, it's not so simple. But then this issue of reproducibility is even more important in MOFs, the discussion that was Silvia commenting. No? So what about this cost issue? No? So you were showing an example, for instance, of a nanoparticle surrounded by a very nice MOF, no? That is super expensive. So do you really think that even if you have a good result, you would be competitive to a more mature catalyst?
Yes, this is another part of the story that, of course, has to be considered for practical application. However, this MOF is not very so. The difference can be really huge in terms of the properties. And then if you have the possibility to use for many cycles, if you have so I would not put the cost at the first issue. So there is a huge amount of material where the linker is not so expensive. Of course, the possibility to buy the linker without having the first step of the synthesis of the linker is relevant. But in the same way, also for zeolites, is the request to have the template. If it's not a commercial template, in some cases where you need to make low aluminum content zeolites, also the adamantane or those are also expensive at the end. But so for me at the moment, the cost is not the major issue. Is the chemistry the major issue? Sometimes it's too nice pictures, only cartoon.
Good, thank you. Very
good. Thank you, Silvia. Your clear presentation and your clear answer and perspectives. Yes, to be frank, in front of the young people, young researcher is one of the major attitude that a teacher, a professor has to take, because otherwise young people will grow with the impression that everything can be done just drawing some few things and go in the lab and see that everything works as planned. It's not a good example of teaching. Okay, thank you, Silvia. Again, thank you very much for your. If you would like to stay with us till the end, we will appreciate it. So you will see how the efforts of this consortium in doing good applications, good materials for applications has been done and getting very good results. And we'll start this parade of showing results from the Multi2ICAT project with Urbano Diaz. Urbano was in the ITQ as a researcher. He had also some connection with Eni in the young, when he was a little bit younger as a postdoc. Urbano decided to be a friend, is a skilled person on preparation of hybrid materials. So he will give us, he will deliver a talk related to synthetic strategies for the preparation of organic-inorganic hybrids for chemical processes of industrial interest. Please, Urbano.
Thank you, Leo. For the introduction, I share my screen now. Okay. Do you see the slide? Yes. Okay. Well, good morning at all. The title of this task is Synthetic Strategies for the Preparation of Hybrid Catalysis for Chemical Processes of Industrial Interest. My idea with this talk is to give some examples about the different synthetic methodologies used in the framework of the Multi2ICAT project to obtain different types of different families with different properties of several hybrid materials, with the objective to use this in different catalytic and tandem processes. This task is focused in the activities performed in the ITQ in Valencia in collaboration with the another partners of the consortium. The first is a little bit to give the initial concept, the significance of the hybrid materials composed by organic and inorganic building blocks mixed, intimately mixed at nanometric scale, forming different porous or non-porous architectures. It is possible to identify the named class 1 hybrid materials when the interaction with organic functions and the inorganic structure is through weak weak interactions, such as van der Waals interaction or hydrogen bonding interaction, and another type more interesting due to the high stability established present in the organic functions is the class 2 hybrid materials, when the interaction between organic and inorganic building blocks are established from coordination or covalent interaction between the different building blocks. The talk about before the Silvia show very well this type of coordinative interactions in the MOF materials, for example. The first step for the preparation of hybrid materials, of course, is the preparation of suitable organic inorganic precursor. I think in this part is I am focused on the organosilane precursors, and the most interesting from my point of view is the disilanes or bridged silsesquioxanes formed by terminal siloxanes groups, very reactive, linked between them with organic bridge in which it is possible to locate different organic functions stabilized in this precursor. With the posterior, the next hydrolysis and condensation of these disilanes through the terminal alkoxysilyl groups is possible to incorporate in the framework of the final material formed different functions. In this slide is show different type of organic moieties, chiral or with chiral and the possibility to incorporate another organometallic complex in the final structure of the materials. This task is very useful, the participation in the project of the case chemical partner, very specific to perform to obtain this type of organosilicon multifunctional precursors. In the framework of the project, we have obtained a great variety of hybrid materials obtained with mesoporous character directly in one-pot co-condensation, or also through post-synthesis grafting through micellar routes. To obtain with this type of methodology, we have obtained a very large families of hybrid mesoporous materials, and even periodic mesoporous organosilicate materials, for example, from University of Southampton, was obtained when only bridged silsesquioxanes or disilane are used as only organosilicon precursors. So a great variety of organic inorganic mesoporous hybrid materials with different functions incorporated in the walls of these solids are synthesized in the framework of the project. Several examples I can show in the next slides to illustrate this type of hybrid materials prepared. Hybrid materials with single site active functions in the framework of the materials, and also I will show another type of bifunctional materials derived of this type of initial single hybrid materials. The first example I can briefly talk is the organosilicious hybrid materials functionalized with aryl sulfonic acid groups. This task is performed in the major part with collaboration with the Università del Piemonte Orientale. It's important to remember that the acidic character of sulfonic groups depends strongly of the organic groups linked close to these sulfonic groups. Organic groups that after are useful to link these acidic functions in the framework of the silicon matrix. It's important the character of this linker close to the sulfonic groups to determine the acidic character of this function. Is now that the presence of the effect of fluoride units close to sulfonic groups, such as the Nafion polymers, is a good example, and the aromacity of the groups close to the sulfonic groups are very important to determine the final acidic character of the sulfonic groups. But up to now, it's not well known the influence of two factors, the presence of fluor and the present aromatic character on the organic groups close to the sulfonic group is not very well studied in the literature, being this matter studied into the multi-2 HiCat project. For this, two types of hybrid materials are prepared with the objective to prepare hybrid mesoporous materials with sulfonic groups pending of only aromatic units, or combining the fluor and the aromaticity with the sulfonic groups with pendant moieties anchored to surface of mesoporous silicon materials. Two strategies for the synthesis of two materials are carried out. The first is the preparation of initially of this organosilicon precursor, starting from this type of sulfonide aniline molecule reacting with isocyanatic groups linked to siloxane units to form this initial precursor, and after using a suitable synthesis conditions in fluoride medium in absence of surfactants and neutral pH and practically room temperature, in soft conditions it's possible to obtain mesoporous non-ordered materials with the presence of the sulfonate groups in the linked to aromatic units present in the surface walls of the mesoporous materials. Another strategy is the preparation of the mesoporous materials using bromide siloxane groups, using the same synthesis methodology based in the fluoride use of fluoride ions as like a mineralizing agent in presence of another silicon source such as thymos in this case, to obtain non-ordered hybrid mesoporous material with bromide pending groups suitable to perform a consecutive tethering reaction with sodium tetrafluorohydroxybenzenosulfonates molecules to obtain finally this type of sulfonate groups linked to aromatic doped 1 fluoride ions in the close to the sulfonate groups. Finally, the exchange process to exchange the sodium cations by protonic forms, this process to obtain the final pendant sulfonic and accessible sulfonic groups in the surface. The characterization of these hybrid materials are performed, being appreciated that from TGA that the stability of the materials is possible to obtain, identify up to 200 degrees. The isotherms of the materials are classical of the type 4 isotherm characteristic of mesoporous material with a pore size distribution around 40-50 Armstrong, and in general the surface area and the total volume obtained is a characteristic, is into the range of the standard of mesoporous materials. The NMR obtained confirmed the structure, the organic groups, and are preserved and integrated in the organosilicon structure, and from the absorption of probe molecules like trimethylphosphine is determine the acid character of sulfonic groups. This information will be told after by the presentation from University of Piemonte with more details about this characterization with probe molecules. Finally, the catalytic activity of these materials was tested for the acetal formation, being identified the material with combining aromacity with fluor groups exhibit a higher activity, showing higher recyclability compared with the material without fluor atoms. Another example that I will show is another family, large family, prepared into the multi-2 HiCat project, corresponding to hybrid mesoporous silica supportive base organocatalyst active for CC bond formation. It's important to remark is well now that in hybrids the base character of the pending of the amino groups depend strongly of the proximity and abundance of external silanols present in the proximity of the base groups. The length of organic linker is also a factor very important, and the curvature of the external surface of the silicon support is factors very decisive to determine the nature and the character base of the amino groups present anchored in the surface of the organosilicon of the silicon matrix. These characteristics are deeply studied for the University of Piemonte Orientale, and for this we have prepared into this topic a large family of mesoporous materials with different amino groups pendant in the surface of the materials, combining or studying secondary amines, primary amines, amines incorporated in heterocycles, and cationic and non-cationic basic groups in the surface of the silicon matrix, with the objective to identify also the more active base materials, with the finality to incorporate in the next step another function to generate bifunctional hybrid catalyst. The first step was such as introduced in the first slide, the preparation of suitable organic-inorganic precursor containing this type of base groups with terminal siloxane groups. The characterization from NMR was successful to confirm the presence of these base groups. This precursor was used in grafting processes using MCM41 support to incorporate this type of base groups in the surface of these hybrid materials. The characterization of the solids confirmed from XRD patterns the mesoporosity character of these materials with different pore size in the hybrid materials finally obtained. This is confirmed also from textural properties. In all cases, with type 4 isoters are obtained with very elevated surface area and pore volume. From elemental analysis and estimation of organic content was concluded that effectively concentration of active site of base sites was consistent among the different hybrid materials. Moreover, preservation of organic moieties was confirmed, but also by carbon NMR when is confined the preservation of the organic fragments present in the structure, and from the silicon NMR is identified also the T species, confirming the effective covalent integration of the organic groups in the framework of the silicon architecture. The catalytic activity was tested for this type of base hybrid materials, confirming that the non-ionic hybrid catalysts exhibiting a very elevated yield and conversion in this type of Novenagel condensation, depending also of the methylenic group used as substrate, and then identify the importance of surface silanols in the reaction mechanism. Also, in this case, the ionic hybrid catalysts are very active in the Michael addition, depending in both cases, in ionic or non-ionic hybrid catalysts, the mechanisms of the reaction are completely different. The third type of families obtained consecutively of this type of single site catalysts are possible to derive to obtain bifunctional hybrid catalysts, in this case by the incorporation of redox active sites in the architecture in the surface of the silicon matrix. It is now the possibility the high energy surface contribute in making them so active in catalysis demanding reaction, but also makes the favor the aggregation of the metallic nanoparticles in the surface of the porous materials. But in the case of the size of the internal porous is suitable, it's possible to avoid the aggregation of these metallic nanoparticles, this metallic cluster even, in the internal porous volume of this type of materials, even with pendant organic species are present in the surface of these materials. It's possible to prevent the migration and leaching of the metallic nanoparticles or cluster. And also these pendant groups can exhibit additional activity in the material, favoring the presence of two active sites in the same time in the same solid. It is the case of this type of materials. The hybrid materials previously showed containing amino groups in the surface of the material. It's possible to incorporate additional palladium nanoparticles in the surface, interacting with these external and accessible amino groups. Dependent aminopropyl moieties play two roles, acting as base in siting in a catalytic process and stabilizing the newly formed palladium nanoparticles within the mesoporous channels, avoiding the aggregation of these nanoparticle species. The X-ray diffraction after the incorporation of these palladium nanoparticles confer the mesoporous character of these materials is preserved. From the magnification of the micrographs obtained by transmission electron microscopy, it's observed that no macroaggregate is observed. And it's important to remark that the mean particle size corresponds to the diameter of the mesoporous channels of the NCM41 used as support, remarking or confirming that the confinement of the palladium redox species into the internal pore volume of the materials. The characterization of these solids from absorption, desorption, nitrogen measurements confirm that it's possible to observe from the isotherms a shift of the isotherms and inflection plot and a lower relative pressures, confirming the effective reduction, partial reduction of the internal pore volume, confirming that the presence of these palladium nanoparticles in the internal pores. And also is logical, a decrease in the pore volume is also observed. Rapidly, this bifunctional catalysis was effective for a target reaction proposed with rhodia in the another partner of the multi-2 HICA to perform tandem reaction based in the condensation of furfural in presence of ketones and consecutive hydrogenation to obtain the final products, combining the activity of the base groups and the redox groups to perform this tandem reaction. And the results obtained are very satisfactory in continuous flow reactor. As conclusion of this short talk, it's necessary to conclude remarking that the necessity of start the preparation of the hybrid materials using suitable silyl derivative precursor to obtain organosilicon hybrid materials with different functions incorporated in the organic bridge of this organosilicon precursor. And after different synthesis methodologies, I have shown for the effective incorporation of these active functions in the porous organic architectures. Finally, I show in this slide a general conclusion to summarize the different routes used during the multi-2 HICAT projects to obtain different hybrid materials, hybrid functional materials. So from suitable DC lanes, suitable monosilanes, or suitable metalloxides, is possible from controlled hydrolysis and controlled condensation obtain unidimensional Boulder subunits that through suitable autoassembly is possible to obtain new lamellar phases, even exfoliated phases, or use directly these one-dimensional Boulder units like for thin fields. Through alternatively from more classical or more standard soil gel routes, through micellar routes, hydrothermal or sorbothermal routes, it's possible to obtain a great variety obtained in this project with non-order, with different structuration level, non-ordered hybrid materials, periodic mesoporous organosilicas, seotypes, coordination polymers, or with the presence of aluminum source, for example, is very elevated, it's possible for organized hydrophilic aluminum silicase. Another approach is the possible combination of individual nanobuilder units, for example, considering the presence of zeolitic layers, for example, in presence of another organosilicon precursor, or even metallic nanoparticles. It's possible to combine these individual builder units to form through multifunctional hierarchical hybrid materials with different functions present in the structure of these solids. These hybrid materials exhibit catalytic application. We have confirmed this into the project. After, in the next slides, will be show the activity of these materials in different examples to produce through more sustainable chemical processes, solvents, flavors, pharmaceuticals, and cosmetics, helping to preserve beautiful, for example, natural space like Albufera in Valencia. This image is the lake close to Valencia. Finally, to give the thanks to my colleagues in the ITQ, especially to Andrea Rigoni, Chelo Hernandez, Candela Segarra, and of course, Professor Fernando Rey. And the last but not the least, to say that it was a great pleasure to collaborate with all partners during the last years in the framework of this very, very, very stimulant multi-tool HiCAD project, European project. Thank you so much for your attention.
Thank you, Urbano. Thank you for your very clear overview. I appreciated very much that you did an overview on of the literature and very few examples of the catalysis that we started, that we pursued in the project. Of course, I just wanted to advise this will is a general comment for all the other speakers. As you may imagine, the best results have been obtained in the last period, the last year, let's say, 6 months. And these are, some of them are not published, not yet published, so, and some of them are pending, may give some patents, and for this reason we cannot disseminate not yet the results, but believe me, some results were really very, very relevant. Some of them that have been published will be delivered, of course, but some of them will be still covered by IP issues. So let's move to the second talk, which is let's say, two-voice talk or four hands presentation, because it will be based on structural properties relationship of hybrids by using physical chemical characterizations. There will be two speakers. Ivana Miletto is a research fellow in the department of di Scienze e Innovazione Tecnologica of the University of Piemonte Orientale, and Maurizio Rossi is a full professor in organic chemistry. We intend physical chemical characterization in terms of both experimental and computational tools. Computational tools are used also for to be predictive of the properties of materials. We are used or are now normally used as a tools for understanding and characterizing physical chemical properties. So first we'll start Ivana. Please, Ivana.
Okay, I think it's working. No. C'è un... Sorry. Okay. Let's try again. Okay, now it's working. So when we talk, no, sorry, but there is this ritorno in cuffia. Che ne so. Ah, forse devi... passiamo...
Scusa,
vai.
posso?
Vai, vai, vai.
Non riesco a trovare...
È qui, è qui, è qui.
Ah, il volume.
Ah, scusa.
Sì.
Sì.
Prova un po' adesso.
Proviamo.
Anche con questo.
Due addirittura.
Grazie.
Ok, adesso funziona. Ok, bene.
Scusa.
Oh no, vai, vai. È impossibile. Okay, now it's working well. So when we talk about the structural relation properties in hybrid organic material or in catalyst in general, of course, we know that understanding the structure of a material, it's important to, sorry, they are saying it's not working on the YouTube. Ah, yes, we are not sharing the presentation. Fine. Okay, because we stopped the... Okay. Sorry again. Now?
Yes.
It's okay? Okay. So, when we talk about the understanding of structural material, understanding of the structure of the material is fundamental in order to correlate specific structural features with catalytic properties, of course. And for any kind of catalyst, irrespective of the organic or inorganic nature, the knowledge of available interfaces and active sites is of utmost importance. We know also from the very nice talk of Professor Bordiga that there are available a big set of characterization techniques for purely inorganic or purely organic components. It's not always the same if we think about organic and inorganic hybrid materials, because of course we have some problems of stability and also some problems in defining the actual conformation of organic moieties on an inorganic surface. So which technique can we use? I would like to give just a spot of some of the techniques, of course, not all the available techniques. I would like to highlight that with the actual current advances in transmission electron microscopy, of course, with the aberration cortic, the transmission electron microscopy, with tomography and the cryo-TEM, it's now possible to direct observe the organic-inorganic interface. Of course, aberration corrected high resolution transmission electron microscopy is not a routinely applied technique. So you have to access to specific facilities. And also, you are not observing the catalyst in a, let's say, real environment, because of course you are in vacuum and clean environment. When we talk about characterization that we currently carry on in our labs, some example is the thermogravimetric analysis that, of course, when you evaluate the loading of an organic moiety, it's very important, and as well for monitoring the thermal stability of the organic component that is usually well related to catalytic activity and recyclability of the materials. But what I will present most today is the coupling of infrared and solid-state NMR spectroscopy carried out in controlled atmosphere in order to probe, of course, surface features, but also the hybrid integrity and, most important, to probe catalytic sites. Among the various materials that has been prepared within the Multi2ICAT project, I would like to focus our attention today on these hybrid materials that were already introduced in the previous presentation, and that are organosilicious hybrid materials that are based on pendant fluoro or not fluorinated aryl sulfonic groups on non-order mesoporous silica. First of all, I would like to drive your attention on the different thermogravimetric profile that you already saw in Urbano presentation, but I would like to highlight that beside a similar behavior in absorbing in physics-sorbed water, and you can clearly see different profile, because the urea bond breakage, that is the connecting linking point for non-fluorinated sulfonic acid, is at lower temperature with respect to the ether bond breakage that is characterizing the other hybrid. And this is bringing to a slightly higher thermal stability of this hybrid catalyst that is also connected, as we will see, with a slightly higher resistance to recyclability and in the catalytic conditions. For what is concerning the successful grafting, so the integrity of the hybrid material, of course, with solid-state NMR, we can monitor, in example, the successful anchoring of the organic components on the silica surface by monitoring the silicon NMR, because, of course, we see the T2 and T3 signals that are due to the grafting moieties that, of course, in the normal silica are not present because only the Q signal from the bulk are visible, and the integrity of the organic components are assessed, of course, by carbon NMR. What is really relevant in this case, because we are talking about acid catalyst, is to characterize the acid sites. In this case, it's not as simple or as straightforward as it is when acid sites are part of the zeolite, in example, because of course we can send probe molecules. In example, I had not the data, but carbon monoxide didn't give very interesting information, because the signal of carbon monoxide absorbed on signals was covering all the other possible signals, and there was no direct evidence of interaction with the phonic groups. On the contrary, the absorption of ammonia give rise to the very specific signal of ammonium ion that we can monitor in the low frequency region of the infrared spectrum. But we can also monitor by solid-state NMR in controlled atmosphere. So we did the same experiment, treat the sample, send ammonia, and we can monitor the increase of the ammonium ion signal in the proton NMR and a very slight decrease in the sulfonic group proton in the spectrum after ammonia absorption. This gives us an indication of the presence and availability of these acid groups. But if we want to have an idea of the strength of the different acid groups, we can move to the use of trimethylphosphinoxide as a probe molecules, which allows us to insert our materials in a scale of acidity, because when trimethylphosphenoxide is absorbing on acid sites, we can follow the signal in the solid state phosphorus spectrum, and the larger is the downfield shift of the signal, the higher is the acidity of the material. So for both our samples, beside a high signal of the physisorbent molecule, we can identify the signal shifted to 89 and 90 ppm respectively for the non-fluorinated and for the fluorinated one. And this is an indication of a super acidity property of the material. In fact, if you go to the literature, you see that when TMPO is interacting with the superacid, the shift should be at ppm higher than 85. And as you can see in this image, both our samples, that is the non-fluorinated and the fluorinated one, are with an acidity that is close to the one of sulfuric acid, with a slightly higher acidity of the fluorinated one. So in conclusion, we have demonstrated that by combining, in particular, infrared spectroscopy and solid state NMR with the use of probe molecules, we can evidence the presence, but also the different strength of acid sites, beside a basic characterization, but very important, on the structural integrity of the organosilane units and the real hybrid nature of the silica backbone by carbon silicon NMR. As already Urbano told, these materials are promising in first preliminary catalytic test. In particular, the fluorinated compound demonstrated a slightly higher stability upon recycle, and maybe this is due to the slightly higher acidity character, as well as the higher thermal stability. So before passing the floor to Maurizio, I would like to acknowledge all the people collaborating in these activities, and of course, all of you. And now I will leave the floor to Maurizio.
Thanks, thanks Ivana for this part of this presentation. What I want to say now, very briefly, is that besides the techniques that have been already presented, spectroscopic, microscopic, thermogravimetric, and so on, now we, in some cases, and more, it is possible to use also calculations, theoretical calculations and simulations, get some information about the structure of the systems and the properties of the system. And now we are in the position that the results of computations can be used as another experimental, let's say, characterization that can support the other techniques. So it can be used as a tool that gives us information about the structure and properties of the systems that we are synthesizing and testing in the lab. Of course, there are a lot of different techniques, computational techniques, and now I want just in a few minutes concentrate on the possibility to compute free energies by molecular dynamic calculation. It's not an easy task. Of course, we all know that knowing free energies of processes is the most important thermodynamical information that chemists look. We look for delta G of solution if we want to compare the solubility of molecules, of docking in biochemical systems, of course, delta G of reactions. And for instance, if you want to look at the solvation process or desolvation process, the variation of a free energy when a molecule is get out from a solvent, it is quite easy to compute the energy, not the free energy. The energy can be computed by different theoretical techniques, ab initio, quantum mechanical, for example, DFT, or classical. The difference in this case is essentially in the number of solvent molecules that we are able to put inside the calculation. But even if we have a very good classical force field, so we can use a lot of solvent molecules, it is easy to get the energy. And in some cases, we can pass to something similar to enthalpy if we add also vibrational contributions. So this is something that you can compute simply keeping molecules, the system fixed in some conformation. Once we want free energies, we have to explore in a much more complete way the conformational space of the system. From statistical thermodynamics, we can have a good estimate of the free energy, G or A, depending on what you are keeping fixed, pressure or volume. We can get a good estimate if we know the partition function. But the partition function means that we have to explore the energy of all the microstates of the system. It's a very hard task. We cannot do it in general. But it's easier to compute differences. Because if we have two different systems, two different states, for example, a molecule in vacuum and inside the solvent, most of the conformations of the two extremes are very similar. So when we compare the two systems, molecule inside the solvent or solvent and molecule separated, okay, in this case, we don't have to compute all the partition function, but only the difference in the partition functions. And this can be done if we concentrate only in the variation of potential, the interaction potential, for example, between the solute and the solvent. We can define the two different extreme states when the molecule is alone and then when the molecule is inside the solvent. And we can modify the potential of interaction simply by one parameter, is called lambda in these equations. And if we vary slowly and gradually this lambda, we pass from one situation to the other. In this case, it is possible to define a derivative of free energy with respect to the lambda parameter. And this derivative is linked to this quantity that you see here, which is the average value of the variation of potential inside the system. This average that is indicated here in brackets can be quite easily computed during a molecular dynamics run. So it is possible to evaluate, because this derivative of potential in the easiest case is simply the difference between the two potentials in vacuum and in solvent. So what we have to do is simply to change slowly the interactions between the molecule and the solvent. For any variation of lambda, perform a molecular dynamics calculation and then sum up all the results in order to have the delta G of the overall process. I'm going very, very quick. Of course, we are not, you cannot understand all the steps, but anyway, this is a well-known procedure and much literature of these techniques. We applied this kind of technique also to the systems in the project, in the multi-to-HiCAT project that we were speaking about, and this is quite a novelty for this kind of applications. Here, just to show you that when we prepare the input file for a molecular dynamic calculation, we can indicate a number of, here, in this, this string is these are the values of the lambda that we want to change slowly from 0 molecule inside the solvent to 1 molecule completely in vacuum. For instance, we apply this approach not to the real solvation process, but we wanted to evaluate, to estimate the delta G of formation of an hybrid material in which this carbene catalyst is placed inside some of these porous silica. And what we do is we get the real system with the molecule inside the pore, and then we decouple the molecule and the pore This is lambda 0, this is lambda 1, and then we pass from this situation to this situation by slowly changing the interactions between the molecule and the silica. This is what we get. Varying lambda, this is the derivative of the free energy along the path. I remember that the derivative of the free energy means the average of the V1 minus V0 inside this system. This average changes because at any step, lambda has a different value. So the molecular dynamics runs different for any step because the interaction between the molecule and the silica changes continuously. But they are all molecular dynamics. For the rest, the calculation is always the same. What is changing is simply a part of the interaction between the two systems, the molecule and the silica. And when we get these numbers, we integrate numerically this behavior, and this is the value of the delta G of absorption that we get in the incremental value. You see that at the beginning it grows and then it gets lower. The contributions are negative at the end of the step. This means that at the beginning, when the molecule is strongly bound to the silica, there is a delta G, a positive delta G when we decouple the system. But at the end, when the molecule is almost free, it is convenient for the system to free it completely. By the way, the different trends of these derivatives are automatically computed by the dynamics. At the end, what you get is this kind of results. We can compare the free energy of adsorption, of linking of the molecule in different porous silica with pores, narrow or wide pores or on flat surfaces. And so we could give our colleagues some information about the relative stability of the system depending on the size of the pore in the silica system. And very quickly, an analogous application is in estimating the free energy of formation of a monolayer of tiles on top of metal surfaces. And we want to compare tiles with SH or tile, or whatever it is pronounced. I mean, the radical you get when the hydrogen is eliminated. And the two systems form different monolayers on the metal. To do this process, we had to split the formation process in several steps. For example, get the tile, put it in vacuum, so desorb the tile from the solvent, and then form the monolayer. Or in the second case, get the tile, put it in the vacuum, detach the hydrogen, and then form the monolayer. For any step, we can compute the delta G. At the end, we get the delta G, the overall delta G, of the formation of the various monolayers, depending on the density of tiles or tiles that we are putting in the layer. And this is an example of the numbers of work. Okay, we don't want to analyze the results because I just wanted to show you very, very quickly, of course, this possibility, which is very, very useful for the experimentalists which prepare the systems, because we can predict or interpret the results by saying, for example, the delta G of formation of different systems. Okay, Ivana has already thanked all the collaborators in the DZIT research unit. So for me, it's just to thank you for your attention.
Okay. Okay, thank you. Okay, time is running. We are a bit late, so I don't think we can. We need to go to the next talk, which will be delivered by Robert Raja. Professor Raja is a full professor at the University of Southampton. He led one of the participant of the project, and is very expert in besides developing new catalysts. But I'm very much impressed. We are all very much impressed in the consortium about his capacity to transfer scientific results to technological innovation to industry. So just demonstrating he has more than 50 patents. So Robert, the floor is yours. Can you hear me?
Yes, I can, Leo. Give me a minute. I'm not able to find my presentation. The joys of
Okay.
Does it work? Can you see my slides?
Yes, Robert. Good.
Is it okay?
Yes, it's fine. Thank you.
I can't see my own screen, so I'm going to do it blind. Okay, so thank you, Leo, for the introduction. So as Leo had mentioned, our role in the project was to look at the optimization and the validation of these hybrid catalysts, which were prepared by the partners, specifically by CSIC ITQ in Valencia, and try and look at applications which would be of value to our industrial partners, Almirai and Solvay, who were the industrial leads on the project. So I was obviously supported by our two very able postdocs, Dr. Marta Mietza and Dr. Anish Lazar, and Professor Ramon Rios gave us guidance on the organic applications and side of things. So just wanted to highlight to you what the main objectives for us were during the project. Apart from validating the catalytic results, we also designed and synthesized some materials. And these were mainly support architectures of the type which Professor Silvia Bordiga mentioned in her opening talk. So she talked about zeolites and metal organic frameworks. Our role in the project was to make hierarchical supports. So these are supports which have both microporosity and mesoporosity. And using these soft templating strategies, we can control the dimensions of the micro and mesopores. These would then serve as handles for immobilizing both organometallic and organocatalytic species. So we are immobilizing active sites within these support architectures, and we would like to do multi-step reactions with these multi-site active sites. And of course, we want to validate these hybrid hierarchical materials in applications leading to fine chemical or pharmaceutical sort of character. And we want to validate them in mostly carbon-carbon bond forming reactions, as that was one of the main objectives of the multi-2-HiCat project. In terms of the optimization, we looked at a range of process variables and catalyst variables, and we tried to use the characterization data, which was provided from the University of Piemonte Orientale, to make some structure property correlations and look at some mechanistic prospects. All this was done with a view to establishing a feedback loop so that we could optimize the catalyst design and synthesis. So I'd like to start by really introducing our strategy for making hierarchical materials. So these are based on the 200 or 240 odd zeolite structures, which Professor Bordiga showed in her opening slide. So we take inspiration from zeolites and zeotypes, mostly aluminosilicates and aluminophosphates, and we embed a soft templating strategy to introduce the secondary porosity. And the way we do it is to use amphiphilic surfactants. So these are surfactant with long tails, and one can use the size of these surfactant molecules to control the architecture of the secondary pore, in this case, the mesopore. In this case, I'm giving you an example of an alpo-5. This is an aluminophosphate number 5. It's a zeotype. And as part of the synthetic process, you keep the same process which you use to make the microporous material, but you introduce this surfactant during the synthetic procedure, so one can start to create the secondary porosity. This strategy enables one to mimic the catalytic properties of the microporous material with the advantage of having these interconnected mesopores. So one of the fundamental challenges in catalysis really is mass transport. And with the zeolites, which Sylvia talked about earlier, one obviously runs into mass transport problems or kinetic thermodynamic problems when you start to introduce bulky substrate molecules. As part of this project, we were looking at fine chemical and pharmaceutical applications, and this entails inherently using bulky starting materials. So having these hierarchical motifs would be quite useful in terms of looking at applications which can happen in the vicinity of an active site within a confined pore aperture, but having still the enhanced diffusion and mass transport. So the procedure is very similar to how you make zeolites or zeotypes. And then you form the secondary porosity within the confines of this microporous cavity or channel. And when you calcine, you can remove this surfactant molecule to leave sort of micropores which are interconnected with mesopores, as you could see there. So in this case, here is a typical micropore of an aluminophosphate moiety. The pore aperture here is about 7.3 angstrom. And if one wants to enhance your mass transport and diffusion through this soft templating approach, we have introduced this mesopore here, which is about 30 to 40 angstrom diameter. So this is very similar to your mesoporous MCM41 silica type materials, which have these pendant silanol groups which line the internal walls and cavities of the pore. So using this surfactant approach, having this silane head really here in the head group gives us dual benefits and advantages. So apart from affording this secondary pore in the vicinity of this micropore, when you calcine the surfactant, you line these inner walls or cavities with these pendant silanol groups. Now, these silanol groups can impart some acidity, but also in terms of this project, it can serve as a functional handle for covalently anchoring organometallic and organocatalytic entities. So going to the structure gives us many benefits. So you are expanding the scope to look at mass transport diffusion, sort of overcoming mass transport and diffusion limitations with the secondary porosity. But through the same one-step process, you are creating these functional handles for the covalent attachment of organometallic and organocatalytic entities. Now, this was one of the fundamental objectives of this multi-to-HiCat project, is to achieve hybrids which can be robustly anchored to porous solid structures. One of the problems which one sees with other methods when you use ionic methods or you absorb organometallic entities is the propensity for leaching. But with this covalent strategy, we went out to achieve more solid, robust catalysts, which could be amenable for industrial validation. So just to give you an example of a recent paper we published with colleagues in Alexandria, we have designed this hierarchically porous SAPO catalyst. So this is a SAPO 37 structure, which is analogous to the zeolite faugisite. So this is zeolite X or zeolite Y, which has been used for the last 40 years in petrochemical refining. So this is a well-known, well-studied material. What we introduce now is, through our soft templating strategy, is these mesopores. And one can use some standard techniques to look at qualitatively maybe what the structure looks like. So if you look at the X-ray diffraction, you see that the hierarchically porous structure has an X-ray diffraction pattern which is identical to the microporous structure, but then you see this broad peak at low angle, which gives you some sort of indication that there is a hierarchical mesopore in the near vicinity. One can then also do nitrogen absorption studies, again, conventional studies, and you see the microporous material really has got no mesopores, whereas the hierarchical variant now has these typical hysteresis loop, which confirms the presence of these mesopores. But one of the fundamental questions which still arises is how interconnected are these micropores and mesopores? And in order to look at that, we looked at some enhanced characterization methods. So here is a technique known as positron annihilation lifetime spectroscopy, or PALS in short, where we use positron molecules to bombard the micropores and mesopores of your catalyst. The idea then is to look at the free spaces, pores, defects, voids on the material, and then you can follow the lifetime, the tau values of this positron decay, and you can start to map out what the pore architecture might look like. So with this SAPO37 catalyst, we fired them with these positrons, and we looked at the decay of these positrons within this particular structure. And one can see here the similarities. For example, in the intrinsic porosity, so we know that our hierarchical material has a porosity which is intrinsic to the microporous system, but then it has this well-defined secondary porosity, which is really in the close vicinity to the microporous architecture. So the peaks you see there are really attributed to one of these signals, the voids in the micropore regime, which is really interconnected to this mesopore regime, which indicated by the tau value decays of this particular structure. So we can see that, interestingly, the hierarchical systems has got much fewer micropores, but considerably larger mesopores, which could be used for mass transport. So this is the sort of the background in terms of how we made these hierarchical materials. And what I want to show you here is one example, which we carried out as part of this project. So we anchored these carbene moieties, in this case, this is a benzimidazole moiety, to the inner walls, to the internal silanols of this hierarchical structure. And we followed the benzoin condensation, which is one of the target reactions for this particular project. So we wanted to see whether you could form this furoin intermediate with high yields and high selectivities. So one of the main objectives of the project was to maximize fundamentally recyclable and stable across many porous structures. So our partners in Alexandria had a slightly different approach as to how they made these hierarchical systems. So we followed the soft templating approach. So we went bottom up, whereas they had a hard templating strategy where they went to a top-down approach. So they took conventional zeolites, in this case, this zeolite, and we contrasted that with an aluminosilicate analog, which is the SAPO5 analog, of which I showed you an analogous synthetic strategy. So through the anchoring of this benzimidazole moiety to these silanol groups within the hierarchical structures, we see this enhanced conversion, but we also see that the ZSM5 hierarchical structure is far more stable and can be recycled quite effectively, paving the way for the industrial validation of these types of catalysts for the benzoin condensation reaction. The other types of material quite closely to what Urbano mentioned during his talk. So he talked about organosiliceous materials and hybrids. In our part of the project, we went on to make both organosilicas, or just pure silica type materials, having organic groups within them, but also organic aluminosilicates or organoaluminosilicates. So this also closely mirrors the zeolite world, which one sees, but then through this periodically ordered structures, one can create mesopores, which could facilitate enhanced mass transport or diffusion. So the synthetic strategy here, again, is analogous. It's well known in the literature. So you take the surfactant molecule, really, which is important for scoping your larger mesopores within the system. You introduce in the synthesis along with a base and a solvent, and then you introduce your organosilane moiety. This is the moiety which bridges between these two silanol moieties and introduces an organic functionality in the intermediate positions where one can tune the hydrophobicity of a particular catalyst. So we are now looking at another descriptor within the validation process is to probe the influence of hydrophobicity. So here is an example where you just introduce the organosilane moiety, and you can embed these organic groups within these periodically ordered mesoporous silica. Now, if you want to introduce some acidity within the system, you could make these periodically ordered aluminosilicate materials where you can replace some of these silicon atoms with an aluminium site. So now you have almost a bifunctional catalyst. You have an acidity introduced within the material, which can work in concert with these hydrophobic groups to impart some interesting catalytic trends and potential. So I don't want to go through the synthetic details in great detail. So what we did was introduce different types of hydrophobic entities based on their size, for example. So here you have an ethyl functionality, you have a benzyl functionality, and then you have a biphenyl functionality. So as we increase the size of these organic linkers, as we call them, one also changes the overall hydrophobicity of this material. And having these SiO bonds here within these structures makes it possible to covalently anchor these benzimidazole moieties, which I showed you on the previous slide. So now you have this organocatalyst, this benzimidazole catalyst, which from the previous slide was attached to a hierarchical structure, which was mostly hydrophilic in nature. We can now start to impart different degrees of hydrophobicity within this particular material type. So these periodically ordered mesoporous silicas also have these enhanced pore apertures. So you have this pore aperture of about 40 angstrom there, which can help with the mass transport and diffusion. And they have reasonable surface areas compared to zeolites, which means one can get quite good catalytic rates and turnovers. So we looked at the same reaction. Here is a benzoin condensation to produce a fluorine intermediate. And in this case, we are now articulating the degree of hydrophobicity through the introduction of these different functional groups. And clearly we can see that when you go from this ethyl moiety,
We lost Robert, huh? We lost Robert.
Probably the Robert connection is gone. We need to wait a little bit.
Serve per capire come mai funziona le cose così. Prova? Sì, adesso va. Questo adesso va,
Okay. Okay, we should advise. Hi, Silvia. Okay, Silvia should go. I think it's as a exam session, if I understood. Yeah, okay. Ciao Silvia. Un grande abbraccio Silvia. Speriamo di vederti qua in villa, prossimo meeting, ok? Hai visto cosa hai perso? Brava. Prossima volta combiniamo meglio. Ciao. Hi, Erme. Welcome. So we missed.
Hi, Leonardo. How are you?
Hi, Erme.
So
waiting for Robert. Here he is.
So Leo, when did you lose me?
When you shared the presentation, I will tell you. Okay, well, the previous slide, you were showing the catalytic results of different hydrophobic systems.
That one.
There, right. So we were discussing that.
I'm sorry about that. I don't know what happened. Was it that slide?
Yes, correct.
Okay. So what I was really showing here was by introducing these different hydrophobic moieties, one can significantly enhance both the catalytic activities of these materials, but also their recyclability. And then I went on to explain some of the structure property correlations that we had established as part of this project. In particular, with these kind of periodically ordered mesoporous silicas, one can probe the hydrophobicity, as I showed you earlier, but also one can start to introduce acidic sites. So one can look at more challenging reactions, such as this particular reaction, which looks at the dehydration of fructose to produce the HMF moiety. Now, this reaction is quite important and it's been widely studied. But what we wanted to show you here was look at the real synergy which one can bring into play in terms of these particular active sites and how they could be effectively used to maximize their catalytic potential. So compared to the previous set of materials, with these materials, we now introduce an aluminium functionality. So we make periodically ordered mesoporous aluminosilicates, for example, as opposed to the purely periodically ordered organosilicas. And then we have looked at this particular target reaction, which is the dehydration of fructose. Now, what we see here is when you have purely just the hydrophobic entities, as you see in here, so this is the periodically ordered mesoporous structure, having the phenyl groups, which impart the hydrophobicity, which I showed you on the previous slide. Now, this catalyst is completely inactive when you look at the dehydration of fructose. Using purely acidic materials, such as these aluminosilicates, gives you some activity, but this is quite low when you look at traditional zeolite-based systems. And then we are introducing here these hydrophobic moieties in addition to these acid sites. And one can now see that when you do these with both the PMO having the ethyl groups or the PMOs having the phenyl groups, we can see that the catalytic activity is significantly enhanced at temperatures as low as about 100 degrees. Now, this dehydration is normally carried out with zeolites at quite high temperatures, but when you introduce this synergistic phenomena with the hydrophobic sites in close proximity to this acid sites, we see this huge enhancement and stabilization in the catalytic behavior. We can then start to rationalize the degree of this hydrophobicity by looking at how the turnover numbers compare as a function of their catalytic potential. So if we look at the pure aluminosilicate analogs, they're quite low. But as you increase your degree of hydrophobicity in concert with the acidity, we now see this significant enhancement in catalytic turnover. So the conclusion really from here is, as part of this project, we can use our descriptors quite cleverly within these porous structures to bring into concert the synergistic effects of the hydrophobicity and the degree of acidity. Now, one other theme within the project was to discover and design heterogeneous asymmetric catalysts or catalytic hybrids, and use these also for fine chemical and pharmaceutical applications. So the rationale for this goes back to some earlier work which we did. So this is kind of work we did with mesoporous silica type materials, which have pendant silanol groups on the internal surfaces, to which you could tether an organosilane moiety. And then one can start to introduce organometallic complexes, such as the one showed here. So one can take a palladium ferrocene-based complex, which is very well-known organometallic catalyst for looking at carbon-carbon bond-forming reactions. You could either introduce a catalytic center, which has a metal, or you could use a purely organocatalytic center, one which does not involve the use of a metal. And I'm going to show you just a couple of examples of how you could use a metal center and one with a purely organocatalytic center. The advantage here is when your substrate now approaches this catalytically active site, it now sees many kinds of interactions. So it sees an interaction with your metal center if it's present, or it sees an interaction with your organocatalytic center. And if both are present, it has a simultaneous influence on both these active centers, but also on the curvature of the internal pores of your catalyst. So what is shown here on the right is really one of these anchored ferrocene systems within a pore architecture, which has a pore aperture of about 30 angstrom. So if you choose a substrate molecule, which is quite bulky in this particular case, this can approach the active site only in a particular fashion. So in this case, it has to approach the active site almost end-on or in a parallel manner to the channel. The size of your substrate molecule, if it approaches in a perpendicular fashion, would mean that it is not able to access the internal active site. So here you are almost introducing a phenomenon, or you're forcing your substrate molecules to bind and interact with your active site in a particular conformation, which is analogous to an enzyme. So I want to show you some examples from the project here, really. So this project was really, this was a collaboration between our industrial partner there, and also our academic partners in Valencia and in Alexandria, and also Cage, which is based in Italy, which made our precursors for this particular catalyst. So what I'm showing you here is one of the hybrid platforms, which was made by our partner, and we complexed palladium to this binap configuration in a manner which is almost analogous to the DPPF, which I showed you on the previous slide. So I'm going to just show you an example here of a carbon-carbon bond forming reaction, which is the Suzuki reaction in this particular case. And here we can see that by changing our process variables, in this case, the temperature, one can significantly validate the merits of this catalyst for working at high conversions, high yields, and high recyclabilities. One can then start to map your active sites in terms of their turnover numbers and start to get to quite low concentrations or optimal concentrations, where you ensure that the site isolation you achieve through your anchoring process can give you a process which is suitable for industrial implementation and validation. So this is one example in the project, which is a real highlight. And as you can see, this involved pretty much all the partners on the project. So it shows how this multidisciplinary team really worked together, bringing together all their strengths in order to achieve one of the most important objectives in this project, is to look at both cascade and tandem reactions. So the catalyst which we used here was again the same one as I showed you as an example. So here I showed you an example of the benzoin condensation reaction in the previous steps, in the previous slides. So here I'm showing you an example of how we could use that same catalyst with a slightly tuned functionality and anchored to a slightly different porous supports. We could see that we can bring in the advantages of this organocatalytic entity in combination with the support characteristics to look at the one-step conversion of this furfural to give you the oxidized product from the furoin or the fural product. So the key merits for this reaction in terms of the project was for us to show proof of concept that one can do a benzoin condensation followed by an oxidation using the same catalyst within the system, which we call a cascade. In this case, we have an example of a tandem reaction where we're looking at a Suzuki aldol tandem. In the first step, we can perform the Suzuki reaction using this palladium active site, and you could make the Suzuki product. And in the next step, you introduce a ketone into the system, which is why it's called a tandem. And with this combination, you can make very high yields of your aldol product. So clearly, using the same catalyst, which is the palladium platform, which we have involved, we have got two examples of a one-step multi-site, multifunctional system, which delivers the objective of the multi-to-HiCat project. And finally, just to give you an example of how the strategy we use for the anchoring of the asymmetric heterogeneous catalyst has panned out. So I'm showing you one of the results from an asymmetric cyclopropanation reaction. It's a well-known model reaction in the literature. So people use this as a benchmark to look at the catalytic properties of your reaction. And mainly this has been accomplished with a range of organometallic catalysts. But what I'm showing you here is two examples of an organocatalyst, which has been anchored using the same strategy as I showed you earlier to the inner walls of a porous mesoporous support. So these catalysts, which we show here, the conversions here might seem quite modest and at times might seem somewhat long, but remember that these do not have a metal active site. So they're purely working on the basis of the chemistry that is involved in your organocatalytic entity. So by optimizing the structure of this organocatalyst and the nature of how you anchor it to the porous support, one can bring into play all these selectivity effects into good harmony to kind of give you enantiomer selectivities which mirror that of the homogeneous catalyst. So if you did this reaction without the support, you would get similar EEs. But now you have the added advantage of using this catalyst in a recyclable manner. So you can recycle this catalyst many times and you could retain the high enantiomer selectivities. So probably with that, I should just summarize the key highlights of this particular project, which we have been able to achieve. So multi-to-HiCat really was meant to deliver a multi-site, multifunctional hybrid catalyst. And as Leo outlined at the start, we needed to do multi-step reactions in a single step, as in a cascade or in a tandem fashion. But more importantly, you want to get high activities, close to 100% as possible. And more importantly, have these catalysts as recyclable as possible. So during this project, we have showed that we could deliver catalysts for many of these reactions, which involve a cascade or a tandem at high conversions, approaching 100% and approaching very high, 90+% in terms of their recyclability. And as the other partners, as Urbano has showed you in his talk, we have also worked on the catalytic testing of their Brunstad acid catalyst. We've also looked at primary and secondary amine moieties, which can be anchored using to the hierarchical supports. And you could do interesting chemoselective and stereoselective carbon-carbon bond forming reactions. Looking at the catalytic descriptors was quite important because that helped us to establish structure property correlations. And taking the strategy to look at novel asymmetric organocatalysts was one of the highlights of the project, as we were able to map the performance of the homogeneous catalyst to that of its heterogeneous analog for validating important examples in fine chemical and pharmaceutical worlds. So I just end by thanking all the partners on the project, and I hope I've showed you at least one example. There were several, and I don't have the time to have showed you those examples, but I showed you at least one or two examples where all the partners in the project pretty much contributed to how we validate these catalytic descriptors in order to take these multi-hybrid catalysts onto an industrial validation platform, which hopefully would be exploited by our industrial partners, Solvay, Rhodia, and also Almirall within the project. So with that, I'd like to thank you for your attention, and I apologize if for the breakdown in the communication.
Thank you, Robert. Well, you showed very good example of the activity in of the consortium. So thank you very much. We should go faster on the next presentation. We are running a bit late, so Herme, you should have some. We should wait a little bit for your presentation. Okay, so the next is. Mark Peratitus. Allow me to say that Mark is a brilliant much younger than me, a researcher, and so I like to emphasize that he did a very rapid career since his PhD in 2006 in Barcelona. Or in Madrid, sorry, and he moved from Madrid to CNRS,
Barcelona,
then to China, and then to he was appointed a few months ago as a full professor in the University of Cardiff, at the Cardiff University. So a brilliant career. So please, Mark.
Thank you, Leo, for that kind introduction. I don't know, you see my pointer, no? Moving? Do you see it? Like, sorry.
Yes, we can hear you.
But do you see my pointer?
Yes.
Very good.
No,
so,
the pointer, no.
No, you see my mouse.
Ah, yes, okay, mouse.
Okay, very good. So this is enough to start. So thanks, Leo, for the kind introduction. So welcome, everybody. Good morning. So a pleasure to be here to give you some details of our contribution in the project. And the title of my presentation is Single Reactors, Tandem Processes, an Insight into multi-HiCAD developments. So the work that I will present were developed in the E2P2 lab, a joint lab between Solvay and CNRS in China, in collaboration with all the partners, most of the partners. So our main vision for the future is that our economy is changing, and we are moving to an economy that will be circular, completely circular. This means that we need to produce all the chemicals that we use today, solvents, surfactants, lubricants, additives, in another way. So we have to valorize feedstocks based on essentially on non-edible biomass, but also we need to valorize waste, essentially plastics, very important to valorize. And in this strategy, we need to integrate small molecules. Small molecules that can be hydrogen issued from water splitting and photovoltaics, so from solar energy. We need to implement small molecules like ammonia, H2O2, oxygen, and also valorize CO2. So this is the key milestones for the next, for our generation and for the next years, is how to integrate everything, all these elements in the chemical industry. But of course, this means that we have to design new processes. And in the design of this new process, the catalyst is a key element. So a key element of this strategy is to design an eco-efficient process that can go with, to design eco-efficient products. That's why our lab in Shanghai was called Eco-Efficient Products and Processes. And we want to tackle these very, very strong challenges in terms of catalyst design. Of course, we need high selectivity and productivity, but perhaps even more than with the standard catalysis for standard reactions, for fossil-based reactions, because usually if you want to tackle molecules from biomass, you will have a lot of functional groups. So selectivity usually is a target, is an issue. Of course, stability and recyclability. In many cases, when you want to tackle a reaction encompassing a platform molecule, you will see very, very fast that your catalyst is not stable. This is very typical. Of course, the issue of energy. We want processes that don't consume much energy as possible. This brings us to design of processes working at low temperature. Here we have the idea of enzymes or bio-inspired catalysts. And of course, we want to design eco-efficient green processes, integrated, intensified processes. And that's why the idea of the cascade in the one pot appears to be very pertinent. And this is why all the technology, all the know-how developed at the multi-HiCAD project is very pertinent because it goes in this direction. So I will not give you all examples of cascading and one-pot reactions that we could develop and that we have developed in our lab. I will just orientate to all the examples and also examples developed in the context of the multi-2 project. And all our strategy focus essentially on working around furfural. Furfural is a molecule that is bio-based, issued from the dehydration of xylose. So from this molecule, you can prepare many other molecules. So you can prepare amines here on the right. We can prepare alcohols. We can also open the ring and have diols. Here on the bottom, we can do CC coupling. Robert was talking about this, CC coupling, to create the molecular diversity of our furfural. We can play with this molecule. We can open totally and create hydrocarbons that could be potential fuels. The dream would be kerosenes, because this is a real target, a real challenge for planes. Many potential things that we can do. Additives, surfactants, biosolvents, polyamide. I feel that is totally increasing in the last years. So one of the first ideas, one of the first concepts that we tried to develop in the past was how to prepare amines from furfural. So one of the things we can do is to take furfural, one ketone, that is methyl isobutyl ketone, and transform this into an amine. Of course, if we want to do this in a single reactor, the main idea is not to isolate the amine. Okay, do you see me in echo, no? It's okay? Okay. So, if you want to run this reaction, first of all, which kind of molecules we can produce? We can produce different when you want to aminate this aldol intermediate. So we can have amination on the carbonyl group. We can hydrogenate just only the double bond. We can have also hydrogenation of the ring. So in the end, we can have 3 main amine products and 5 intermediates. So which is the relative stability of all these molecules? So TFT gives us some insight. So this is just a thermodynamics. I don't show barriers. It's just a thermodynamics. So we start by this molecule here that we call 1A. And depending on how we aminate the molecule, we can have different range of stability. What we see is that the more we hydrogenate the molecule, the more stable it is. This is logical. So this molecule here on the right should be the most stable one. So if you design a good catalyst that is active, that would be the molecule that could be prepared with higher selectivity, because it's this the end product. To stabilize molecules in the middle would be more difficult. So we would need here more to target a catalyst with higher selectivity for intermediate products. In what concerns the aldol condensation, there is not much work. Most of the work concerns furfural with acetone. And this reaction, you can run it in a single reactor in a one-pot fashion. You have different examples of catalysts. I didn't provide the references, but essentially you have groups more or less around the world working on that. Most of the catalysts focus on these couples, zirconia and magnesium oxide. It's basic catalysis. We can run the reactions at between 50 and 180, 140 degrees centigrade degrees. Some zeolites can also be useful, basic zeolites. In terms of acid zeolites, you have less amount of examples. In our case, our first entry into the system was to use Upperlist 26, that is a basic resin that shows capacity to do aldol condensation between furfural and VK at mild temperature, at 80 degrees. We use that. It is the structure. So let's eliminate this aldol product, which is the products we can obtain, because this depends a lot on the catalyst. So if we use ruthenium, you will form essentially this end product here. Okay, so you don't use organic ring. Platinum also the same behavior, but worse balances. Okay, yeah. And the best is essentially platinum aluminum. That gives us the end product, as I was showing, the most stable product in the thermodynamic analysis. What about the experimental conditions? Horrible, right? Okay. So can you close all the macros, please? Okay, I continue. So close all the macros, all the microphones. Okay, I continue. So The temperature will influence a lot the catalytic behavior. This is for palladium alumina. We'll see that 120 degrees is a good temperature. And also the ammonia pressure will contribute to these results. So we optimize the conditions. We can have product 4A, the most stable one thermodynamically with high yields. Here you have the kinetics. You see very clearly that product 3A is an intermediate. Okay, yeah. Here you see it. And from this product, from 3A, you obtain 4A. Okay, this is how it works, the mechanism. In terms of recyclability, you can have recycling for at least 2 steps. After the different steps, so the catalyst loses activity, loses hydrogenation activity, and you don't hydrogenate so efficiently the furanic ring. Okay. What is very important is that we don't see leaching in this in all these applications. Unavoidably, this kind of catalysts have some formation of oligomers during the reaction. You can see very well by TGA and infrared pictures of these oligomers on the catalyst. In particular for palladium, we will see always some sintering. Amines promote sintering of palladium. So even you can see things like this. So sometimes you don't see a lot, but small rocks like this. So amines tend to agglomerate the palladium. So this is something that has been well studied. But however, if we optimize the condition, we can have decent results in terms of the recyclability. And when we put fresh catalyst, somehow we can recover the catalytic behavior. We can have some scope to different kinds of amines, aliphatic, with different kinds of number of amines, with decent yields. And now with this result and combining with the Amberlist 26, we can really design a single reactor process. So the idea is that we are going to integrate in our reactor furfural and MeVK, the 2 catalysts together, and then we're going to inject ammonia and a hydrogen later. And so when we do this, so the first experiment, we just start by the intermediate, so we have 97% yield. Now in a single reactor, Amberlist 26 palladium, the yield is 60%. Let's optimize a little bit the conditions. So we can move now to 75, 74 by playing with the amount of palladium and the time and the hydrogen pressure. And now if we really optimize the system, especially the MeVK furfural ratio to 1.2, the yield is excellent, 85%. So yes, we can integrate all the elements in the same reactor. We can run them in a single one pot. So we don't need to separate furfural, this intermediate, this aldol intermediate in our process. Okay, this was the first example of a single reactor process targeting an amine product. What we see is that we need this Amberlist 26 to operate. This is a catalyst that is not very stable, it decomposes. So along multi-2-hacket process project, we discussed on potential catalysts that could be more stable and that somehow should not work with basic catalysis because this is what was working in the literature. Can we do something a little bit different and very stable? And then it came to the idea to use different kinds of zeolites. And for the model reaction now, we're not going to use an amine. We're going to make it more simple, just hydrogenation in the second step. So with the support of our colleagues from UPO in Italy, we prepared different zeolites. Here, these are just commercial zeolites, the first ones we tried, just to show you that the yields in the conversion is low, except A-type zeolite, Fauger's-type zeolite. When the aperture is higher, when the cavity is higher, 70.4 angstrom, the conversion apparently is higher. So it seems that this pore accessibility is something important to run this reaction. In all these cases, we see 2 byproducts that we didn't see before for the amines. So this means that this acid, this bronzed acid activity, catalysis that we have is promoting also this byproduct formation. So now we used, by the advice of Enrica and Ivana, their big expertise on the SAPO materials. So let's try to see if these materials could work because the pore aperture is similar to wild-type zeolite. And what we see is that depending on the silicon amount, you see similar results, 49, 40. But if you make this hierarchical now, the situation changes. So the pore aperture is important, but also the fact that you have mesopores in the system, you can increase really the catalytic activity. When we compare this to a standard, just a benchmark catalyst, SBA 15 catalyst, only mesopores, you see that the conversion is lower. So it seems that this hierarchical structure of this SAPO material with its good pore aperture and the acidity that this solid is capable of generating could be something promising for the project. So we try to explore this material more in detail. We did a lot of work in terms of kinetic experiments. So just to summarize, the best catalyst was this catalyst with 0.9, silicon 0.9. We see always in terms of selectivity for our target product a plateau, more or less at 60% selectivity. What is very interesting is that the conversion, when we compare these straight and dotted lines, that is hierarchical and not hierarchical, we are always much more active than when we have the hierarchical structure. So the optimal conditions were 160, 180 degrees, and we stick to these conditions. We have also explored other samples, hierarchical, not hierarchical, other temperature, and this was found the best conditions. We also can see the same results by plotting the selectivity conversion curves. So you see very clearly here for a standard sample, the conversion is much lower. When the hierarchical material is used, the conversion is much higher. Selectivity always with a plateau at 60%. We can reach this plateau much faster with a hierarchical material. So here I'm plotting in this table, yes, I'm just comparing the initial reaction rate. We just measure the TOF, the turnover frequency for the different catalysts, for hierarchical and not hierarchical. So the bigger this number it is, the more reaction rate you have compared to the microporous material. You see that for 0.9, the difference in rates is spectacular. We can even have values at 30 times faster with a hierarchical material compared to a non-hierarchical material. We also measure all the apparent activation energies. The activation energies that we have are not very different. Even if the reaction rates are different, the apparent reaction rates are not very different for different materials, more or less about 80, 90, 100 kilojoules per mole. So it's a reaction that requires some temperature to be operated. In terms of recyclability, we see that after the first cycle, we have some drop down, more or less stable, but by calcination, we can increase the activity, which points out that the main deactivation source of this catalyst comes from formation of heavy products blocking the access to the active sites. Here, the colleagues of Italy were very skilled and helped us to characterize a lot the different types of acid sites and silanols that we have in our system. So we could characterize all the material. We have essentially two main acid sites in our sample that we could list and compare between microporous and hierarchical. So we have complete characterization. But what's very interesting is this test between using ammonia and static hinder pyridine that could allow us to distinguish between sites inside and outside the micropores. Just by doing some basic calculations between these two reagents, we can compare. What we see very clearly is that here in this table, the values of ammonia, the sites titrated by ammonia are much higher than the sites titrated by this pyridine, which means that most of our sites are located in the mesopore, in the micropores, not outside the micropores. And we could also characterize in more detail these sites by ammonia TPD. Here I'm just comparing the fresh and the spent catalyst. So most of our catalysts are medium strength, and what we call intermediate strength, here located by this descriptor. We have a big band in the beginning that is weaker sites. What is very interesting is that along the reaction, we have a new band that appears. And that points out that somehow we have some hydroxylation of the sample, probably outside the particles in the mesopore domain. Also, with the help of the skills of our colleagues from Alessandria, we were able to elucidate a little bit the mechanism of how this aldol condensation reaction takes place. And it seems that there are two sites participating, one acid site that should be located inside the microporosity and one silanol outside in the mesoporosity, outside the microporous zone. This information came by analysis of infrared, in situ infrared, using MEVK, by absorbing MEVK, desorbing at different temperatures, and also desorbing MEVK and absorbing later furfural. I'm not going to enter into detail, but we see some shift of the CO stretching of MEVK, that is interaction with silanol. Some bands here that disappear or don't disappear. So from all these analyses, we can get all this information. Then if you want to design a single reactor process, we need to put the second catalytic center, the redox center. If you want to do hydrogenation, we need to put palladium in our case. And the first thing we do is to try to see, well, if you put palladium, what happens with the aldol condensation? Are we generating new sites, acid or basic? So the answer is that in our case, no, more or less. What we see is that the aldol condensation follows a similar pattern in terms of conversion and selectivity. So the fact that we put palladium in the form of palladium oxide, because it's not reduced so far, so it doesn't affect this aldol condensation. More or less, we see a similar pattern in terms of the ammonia TPD with intermediate sites of intermediate strength in this zone here, more or less the same pattern in the low temperature region. Now let's design this one port process, this single reactor process. So this is a picture of our very nice particles with a very well dispersed palladium. Now this palladium is outside, is outside the particle. This contrasts what was Urbano showing before. In his case, he could confine the palladium in the mesopores. So it's different, and that affects also the selectivity. In our case, we only hydrogenate the double bond here, this double bond here, and also the furanic ring, but we don't touch the carbonyl group. In his case, he can touch the carbonyl group. This is something very interesting. Here are some results on the single reactor process. So we optimize the first step and the second step all in one pot. The maximum yield toward this product is 45%. To total products is more or less 50%. 50% of all products. We have yield to other products that come from the other aldol condensation products that I showed before. So the proof of concept is there. We can design a single reactor process by combining aldol condensation and hydrogenation. That's very briefly, because I think that I don't have much time. The examples I showed so far concern the development of a single reactor process by combining an acid-basic center with a redox center. We can do aldol condensation and lamination, aldol condensation and hydrogenation. But we can also combine two redox centers to do more difficult things. And this is a very difficult thing. So let's take now, instead of furfural HMF, now we have an OH. This OH is extremely poorly reactive, very difficult to react. So essentially, if you want to do reductive amination, you will obtain this intermediate, but not the second one. Very difficult to find a catalyst that is able to tackle the two groups at the same time. Very, very difficult. So what can you do? Well, you can design a two-step process. So we can oxidize the first OH into carbonyl. So we have this DFF intermediate, and then to do the reductive amination. But why not to do in a single reactor? So we can have the two steps combined together, and then we start by HMF. We don't isolate the intermediate, and then we have the final product. So now we need two catalytic centers, two redox centers, one that does well oxidation, the other that does well reductive amination, and they are not antagonistic. This is the trick. So very briefly, I'm not going to enter into details. So my student was very skilled. He found two catalysts that are not antagonistic. So one catalyst that works well for the first step, that is ruthenium carbon working in dioxane. It's very important in this process that since we're going to work in the same one-pot process, we need the same solvent for the two steps. So we tried also dioxane for the second step, and the good catalyst that is working is palladium carbon. So we can run the two steps separately with the same solvent, one working well for the oxidation of HMF to DFF, and the second from DFF to the different amines. So what he did now is just to combine the two catalysts together and to see if when you put ruthenium carbon and palladium carbon, you can do the oxidation. And the answer is yes. So palladium under this condition is oxidized and is not active. What is working is the ruthenium catalyst in the first step. The same happens for the second step. So the system that is operating is the palladium carbon, the ruthenium is not active for this reaction. So just by optimizing the ratio, in our case 2.8, we can have excellent results only for the second step in the presence of the two catalysts together. So here you have the example of the single reactor process compared to the two-step process. You see that the system works quite well. And with these results, and we have the stability is more or less decent. And what is very interesting from this result is that we could design a real bifunctional catalyst. That is a real milestone for this kind of processing. So in our case, we did something very simple as proof of concept. We just took the commercial ruthenium carbon catalyst, we impregnated palladium, we tried different protocols, and we found that the best optimized system gives us in a single reactor process 68%. So in this catalyst, you have two bricks, ruthenium and palladium. Ruthenium is working in the first step, palladium is working only in the second step. They are not antagonistic. And you have some recyclability in different cycles. So more or less decent results. Just to finish very briefly, key messages that we learned along this project and along this development of these single reactor processes. So these processes are interesting to have process intensification. That is something extremely important if we want to move this to this new economy, to this greener economy. And of course, try to avoid separation of intermediates. And here the support of Solvay was very important because we could quantify all these benefits with very good eco-evaluation and LCA analysis. At ISO yield, comparing two-step processes with single reactor processes, our benefit could be between 10 and 15%. More or less, that could be general for different reactions. But of course, in terms of science, the key point here is to design real bifunctional catalysts, avoiding antagonistic effects between the two different centers, acid-base, redox, redox, depending on the kind of catalysis you want to develop. And for that, for sure, hybrid catalysts, such as those that we develop in multi-2-HiCat, are ideal for that because we can tune very well the distribution of the sites and the compatibility between them. Just before to finish, big thanks to everybody. I have so many people to thank. I hope I do not forget anybody. So first of all, the people of my team, of my lab in Shanghai, Li Gao that did the PhD. Many of the results come from his PhD manuscript. Xie Jiang, that was a former PhD student working on autonomination. Jin Shara, his postdoc. Brad Kuzema, that gave me a hand. He's going to give a talk later, so we'll hear him later. Shanru, that did a lot of calculation in Stanford, is our director of the lab. And of course, I want to thank the funding of multi-2-HiCat and all the friendship, a very good collaboration and discussion among all the partners. I'm not going to mention the people, but everybody you all acknowledge. And I hope that this collaboration can continue in the future. Thank you very much.
Okay. Thank you. Okay. Just an echo. Okay. Can you hear me now? Okay. Thank you, Mark, for your interesting presentation. And now, because we are running a bit late because of technical reasons, so let me propose to skip the break because we are running 40 minutes late. So I asked Professor Hermenegildo Garcia to join us. Thank you, Herme, for your acceptance to join us. Hermenegildo Garcia is a full professor of the University, Technical University of Valencia. His interests are in heterogeneous catalysis and photocatalysis, on which he has a really impressive records of more than 800 papers, 25 patents, 50,000 citations, H-index of 100, more than 100. So he's really an eminent scientist. And I'm very pleased that he is here with us. Herme, the floor is yours.
Leonardo, thank you for your introduction. And I would like to thank Enrica and Urbano for the invitation also. So I will be trying to be fast because part of this presentation probably Silvia has already commented. So I will skip the part of what are the metal-organic frameworks, and I will go directly to the results that we have using metal-metal size and metal ligand size in a MOF, and then I will comment a few examples of tandem reactions that we have performed. So this is the one that I am going to skip. This is a MOF. The important thing here is the large surface area, the high crystallinity, high porosity. And actually, what I would like to remark here is that when you see the structure, most of the volume is empty. Most of the volume is empty, and the number of atoms that you have in a certain volume is the minimum possible. So actually, one of the best things of MOFs is that you have a large porosity, so the lowest framework density. And the other nice things of MOFs that I will comment also in some examples is the functionality. because we have here an organic linker. This organic linker allows us to be modified and also to introduce some functionality in connection with the metal. So regarding catalysis, MOFs can exhibit activity, particularly because we have metals in the nodes. These metals, they have some coordination positions that they are compromised with the framework, but they can have also some free coordination positions. And these free coordination positions make metals acting as acids. But also we may have functionality, and I will show some example of the interaction of both the metal ligand, and the ligand can have substituents, and these substituents can be acidic, can be basic, and then we can introduce an additional functionality. And the third possibility that I am not going to comment due to the time is just to use the porosity and the open voids of the metal organic framework to have some guests, typically metal nanoparticles or metal oxide nanoparticles that have also some activity. So the first example that I would like to comment is this one, just the condensation. This condensation has a special name, is the Prince reaction. And at the end, the product that is wanted is this one, that is nopal, that is has a scent of pine, is a fragrance that is used in detergency because it's the typical, the most common fragrance for smelling pine when you clean the floor. And what happened is that here in this slide, what you can see the activity of different MOFs. One MOF is 1100 chromium, and the other has iron and has other structure. The point was to obtain 1100 with iron, because then the prediction from theory is that this catalytic activity will be higher. But the problem is that it's not possible to obtain 1100 with iron, because then the structure collapses and you have actually this other MOF. So the point is, how can we have the advantage of larger porosity of 1100, that is an open, very open pore MOF, with stability and activity due to the iron? And the answer is that here we can have, sorry for this, I was trying here, we can have mixed metals. Mixed metal, actually we can have chromium and iron, and the chromium is playing the role of providing a structural stability to this type of MOF that is highly porous, while the iron is going to have the activity as metal site. So then the reaction, when you have this, the 1101 chromium iron, then the activity is much higher, and this is the reproducible, because depending on the synthesis, the reproducibility is quite high. This is actually one of the best advantages of MOFs, that the synthesis is highly reproducible. So we increase the amount of iron to reach the optimal, and the optimal is when you have about this ratio, 4 chromium and 1 iron. And when you plot the initial reaction rate against the iron content, what we observe is that it was not linear, it was an increase in activity. And this increase in activity is very interesting, because it's indicating that when you have a cluster, a nodal positioning where you have 2 iron, the activity of 1 iron is increased because the other iron is present. And this is a kind of inductive effect in where the higher polarity of iron is increasing here the positive charge on this iron. The previous example was prepared with 2 metals just from synthesis. But one advantage of MOF is that they are reversible materials you can form, and they are a kind of living materials in where you can modify after the synthesis just by exchange. So here we have another example in where we have the UiO66 that I suppose that Silvia has already commented in detail. And we introduce another metal, in this case the titanium metal. And we use, for a reaction that was not Lewis acidity, was just oxidation. And what we observe is that compared to the one that contains only zirconium, if you have the 2 metals, the zirconium and titanium, then the activity increases. But now moving further, we can also play with the ligand. And if in the ligand we introduce some nitro group, then the electronic positive charge on the titanium atom is even higher, and then you have higher activity. Of course, I am not going to comment in detail, but we have all the characterization of these materials. These materials, for instance, when you move from pure zirconia and you introduce higher amounts of titanium, there is a small shift, a small but clear shift in the XRD, and this is due because the size of titanium is smaller, so then the position of the peak changes to higher levels. Of course, we have also the distribution of the metal, zirconium and titanium, and they coincide. This material containing zirconium and titanium, and also we are modulating the linker, the ligand, can be used for oxidation with oxygen as oxidizing reagent. And for instance, we can form epoxides. This is our best model, cyclooctene, because it's convenient, volatility is low, and it's very easy to determine the formation of the product. And depending on the titanium that you have, the activity increases, and actually in this case of the material, we can go to up to exchange between zirconium and titanium about 40%. 40%. Maybe if we go further, then the activity even increases further. The material is stable, and we have here a productivity test in where we run the reaction for a very long time, and we with just a small amount of catalyst, and we observe an increase up to a complete conversion. Also here we have recyclability test, and as you can see, the temporal profiles coincide. Also the XRD shows that there is no change in the material. I am stressing this because one of the main concerns in the case of the MOFs is stability, and of course we always check. But I have to comment here at this point that this reaction is carried out at not very high temperature, 120 degrees, with solvents that is convenient solvents that they are not corrosive, like acetonitrile. And under these conditions, UiO66 is very, very stable. You can reduce for, I don't know, 100 times without any change, and we did. Here, when you change the linker, and we can introduce an amino linker, or we can have just the proton or the nitro, the activity increases. And if you plot the sigma Hammett constant, that is a measure of the electronegativity of the aromatic ring against the relative initial reaction rate, what you obtain is a linear plot. This means that in this case, for this particular reaction, what we are just monitoring is just acidity without any other role from the substituent that we have introduced, because we have a linear plot. However, in other cases, like for instance this that I'm going to comment now, we observe that there is a deviation from the linearity of the sigma Hammett constant. So this indicates that this substituent is playing a role per se. So here, really a bifunctional catalyst. And this is very interesting because for many times it has been claimed that you need an acid-base pair in the same material, and you have this type of acid and base pairs in the same solid, then you can run the reaction with much lower acid strength. And here we have an example. This example is the acetalization of aldehydes, in where we study the activity of Mil-101 chromium and bury the substituent on the terephthalate linker, and this is the results, that there is a big increase in the initial reaction rate when we have different substituents. I have to mention here that this is the logarithm plot, so this increase is not small. This increase is about 50% of the initial rate, so here the ammonium is playing an important role. Another comment in this transparency is that we always check the performance of the MOF compared to an analogous homogeneous catalyst. And one of the most convenient examples is that to use acetates. Acetates, they are analogs to the MOF, and they are soluble in many solvents. So for instance, if you compare here the activity of the chromium acetate with the MOF, what we have observed is that typically the activity of the MOF is always higher than the homogeneous catalyst. And this is because porosity and polarity of the internal voids increase the concentration of the reagents inside the pores, and because the reagents are more concentrated inside the pores, then the initial reaction rate and also the rate of the reaction is higher. So moving to the bifunctional MOFs and comparison of the metal ligand, again we have here, this is UiO66 with the octahedra nodal zirconia, and then we modify the linker with different substituents. All of them, they have the same structure, so they are isoreticular. The structure is maintained. And this is our proposal, that when you have a basic site, basic site, like an amino, at a certain distance of the acid site, they combine because you are activating the two reagents. In the basic site, you are activating the more acidic reagent, that is the alcohol, while in the acid site, you are activating the basic reagent, that is the epoxide. And in this case, we have the product. The product happens to occur with a nucleophilic substitution type 1, and the reaction is much higher than if you don't have this substituent. And this is because the combination between the cooperation between the Lewis and the basic sites in the material. So again, another example, this refers to oxidation, because what we have observed is that Lewis acids also catalyze oxidation reactions. This is an important point. So acidity can be used to activate oxygen. For instance, here is all the full reaction mechanism, in where what happens is that the active site really is generated a radical, and this first radical that is generated is later moving all the oxygen activation. And really what we have is a chain reaction mechanism. And again, when you have different substituents and you plot the sigma Hammett constant for the initial reaction rate, relative initial reaction rate in logarithm scale, you have a linear line, except when there is a real activity from the substituent. And in this case, again, the amino group has much higher activity. Again, this is a linear, this is a logarithm scale. So this means that we have an activation about 50 times higher due to the presence of the amino group. Tandem reactions, one of the tandem reactions that we have studied is the formation of heterocycles. In this case, benzimidazoles. Benzimidazoles and the reaction starts with the condensation of the benzaldehyde with an amino group. You start with the amino, and the amino can evolve in different ways, and you may have byproducts, or you may have the final product. This depends on how fast goes the oxidation. So here we have acid sites, but also we need an oxidation sites to obtain the final product benzimidazole. And again, there is an influence of substituents on the aromatic ligand, and this we understand that is due to acidity. If you increase acidity, then you also increasing the oxidation activity of the MOF. This reaction can be done with a lot of benzimidazoles, including fused benzaldehydes, or they having different substituents, electron donors, electron acceptors, even heterocycles like pyridine that typically doesn't work with conventional Lewis acids, and also other heterocycles like sulfur, but also aliphatic aldehydes. So this material works well with a very broad scope, making the tandem reaction. This is another tandem reaction in where what we have is a functionality that is oxidation. This oxidation is going to be run photochemically, because one of the activities of MOFs is that they can absorb light. They can absorb light by the ligand. Some of the MOFs, they have color. If they have color, means that they are able to absorb visible light. And with visible light activation, then you can promote the oxidation to the aldehyde, and then the aldehyde condenses, similar to what we have commented previously in the case of benzaldehyde, except that in this case, what we have is nitrogen and sulfur, and what we end up is in a benzothiazole. Similarly to this mechanism also works with benzoxazoles, in where this is an oxygen, and also a benzimidazole. So again, the reaction mechanism involves three steps. Of these 3 steps, 2 of them, they are oxidations. One of these oxidation is promoted photochemically, and the other requires acid catalysis. Well, this material is stable, and selectivity does not change upon reuse, and we have checked that there is no leaching from the metals to the solution. Another example, this is my last example, is light-assisted nitrogen hydrogenation. This is very interesting because we don't use hydrogen. Actually, to provide the hydrogen, we use alcohol. So alcohol is going to give the hydrogen that is here in green. In green, how? Because if you irradiate, methanol is a good electron donor, and then it evolves giving a proton, and this proton finally couples and forms hydrogen. So the light is just a formation of hydrogen. Actually, MOFs are one of the best photocatalysts for hydrogen evolution. So with this hydrogen that is formed in situ, then the reaction occurs, and then this hydrogen is used to reduce the nitro to the aniline, the corresponding aniline, and the reaction occurs in very high yields and conversions. Depending on the material, for instance, this case is one that contains amino group because it absorbs light. Others that they don't absorb much light, they have lesser activity. So this is the change in the color because initially the nitro group is colorless, but you end up in something that has a green color. The material is stable and you can reuse. The temporal profile is the same. The XRD of the material does not change upon reuse. And here is our explanation of why the activity of the nitro group is better, and it's because it's better aligned with the redox potential that is required for hydrogen evolution. So this one that is in red has the redox pair more aligned with those that are required for evolution from hydrogen. And with this, I want to finish. Thanking you for my invitation. I have just a take-home message that after 30 years of MOF, there is still a lot of research on these materials because they have many flexibility and versatility in the synthesis, but also in the properties. And we have published over the years, last year particularly, one review just showing that metal organic frameworks are special materials for multifunctionality. Multifunctionality, that is just the topic of this network, of your network. And with this, I am done. Thank you very much. Thank you,
Herman, for your very interesting lecture. So, and you for spare some time. We have not too much time for discussion. I'm very sorry about this, but
yes, I understand.
Just personally, I would like in the next future, I would like you to have a discussion with you for possible collaboration. Okay, Herman.
Yeah.
Thank you, really. Thank you very much. So now we move to the last two speakers. They will deliver some, let's say, ideas from industrial in the industrial environment. So there are two contributions from Almiral and from Solvay that are two partners of the consortium. The first contribution is from Jose Haigader, Bosch, Pep, nickname. Pep, please.
Okay, thank you, Leo, for this kind of opportunity that you've given us to participate in this webinar on finalizing a multi-tool high-cut project. I will share my screen. Make sure get it right. So can you see? Sorry, can you see my screen now?
Yes.
Okay. Presentation mode, and I will use the laser pointer. Okay.
Good.
So for today's talk, which is a new road, multi-tool high-cut catalyst, a new road to increase efficiency and sustainability in the pharmaceutical industry. I have divided this talk into two parts. First part, just to let you know who we are and what we do. And then second part, which is always going to show you why, as a pharmaceutical industry, Almiral is interested in this type of projects, as you will see that catalysis is quite important to us as well. So to start and to show you a little bit of what is Almiral, just to let you know that Almiral was founded in Barcelona in 1943. It's a bit over 75 years by now, quite a long time. And we are present in very many countries. In some of them, we are not directly present, but we are present through affiliates or strategic alliances that have been developed over these many years of presence. And just to give you some figures on our business, just to tell you that in terms of net sales, we are above 800 million euros per year. This figure was from year 2019. And in terms of employees, we are over 1,800 employees located in different sites. So you can see on the right that we have several centers. We have headquarters in Spain, which are based in Barcelona, in the city center. And also we have headquarters of our US site in Exton, Pennsylvania. And then we have a couple of R&D centers, one of them located in the nearby area of Barcelona, and another one at Rheinbeck in Germany. We also have a couple of pharmaceutical plants, one in the nearby area of Barcelona as well, the other one in Rheinbeck in Germany. And we also have a chemical plant in the nearby area of Barcelona as well, where we prepare active pharmaceutical ingredients. So what is our focus? What is our aim, our objective? So we have a strategy that it's to be a leading pharmaceutical company in medical dermatology, but our end game or our last aim is to help to improve patients' lives within medical dermatology, with people with medical dermatology conditions. And in particular, we are interested in like three main parts, which are immune inflammatory diseases, rare diseases, rare skin diseases, and non-melanoma skin cancer diseases. So one part which is quite important in our organization is the fact that we are fully committed with our R&D. So we really believe in the R&D to deliver new drugs to cure several dermatological conditions. And for this purpose, we created a new R&D center not long ago in 2006 in Sant Feliu, which is next to Barcelona. And our orientation there is to look for breakthrough innovative programs, which are based either with new chemical entities, which are small molecules, as well as new biological entities, or called biologicals, in order to develop new drugs that will be useful for our patients. So in this context, we have 7 programs in early discovery, either early discovery or preclinical stage. We have 2 projects which are in phase 3, and 2 other projects we are currently at registration stage. Besides all these internal programs that we have, we also improve our R&D pipeline by enrich through several strategic alliances that we've been developing through the years. That goes either through premium collaborations with technology companies or collaborations with academic centers that of reference that we can get a common objective. Just to show you what we do in the R&D value chain that we have internally, is just to let you know that we have expertise from all the parts that are involved in R&D chain. So most of you probably know, drug development takes a long time to get a drug into a market. So we go all the way from the initial stages of target identification and validation, just to find what disease we want to get some new drug on, want to improve patients' life, all the way to the finally regulatory strategies that we have to do in order to register a drug, in order to be able to commercialize it and lead it to the patients who need this novel drug. So with this, and just to give you a hint on what is about to develop a drug. Developing a new drug is, first of all, it's a costly and very time-consuming task. There are main hurdles that, especially during the clinical developments, you may envision that, for example, a phase 3 development, sometimes it may take 2 years of giving the drug to patients and fully understand what's about this drug before we can commercialize it, to make sure that it's safe, secure, positive, that we get into the target that we want, and so on. And so you can envision that the largest extensive are usually directly linked to all these clinical trials that we have to perform through different hospitals, different patients, several medical doctors who are all involved in this process. So in this case, the active principal ingredient of the drug, which the manufacturing cost of it, is at the beginning is less significant, and it becomes more significant as the development progresses towards the commercial manufacture. So once we are in the commercial, then the API manufacture is the key driver in terms of cost. But for the research part, it becomes important as the research goes on. But it is important to realize that from our perspective, the drug manufacturer is where we can have a lot of savings, both in terms of cost and in terms of time. So as you probably know, we have a lot of quality and environmental requirements that have been regulated and that we have to achieve and accomplish. So an API manufacturing is becoming more and more demanding as the drug development comes closer to being able to being commercialized or being given to a patient. So for this reason, we need continuous process improvement throughout our drug development in order to achieve this optimal cost and time efficiency on one part, so we can save money and time, and sustainability, so we can comply, we can be sure that we get a greener planet, we get a more sustainable planet. So those are like two key aspects of our research going through drug development. So for this, we need to be acquainted and we need to be familiar with all the technological innovations in order to get these medicines. Having said that, I'm going to move into the chemistry that we perform here and how I hope I will be able to show you why is it important, all the work that's being performed in catalysis. So you can envision a synthesis reaction, which is just joining two reagents, two starting materials, green one A with a blue ball B, to get a complex, AB complex, usually through a covalent bond. But for the pharmaceutical industry, this is more, A and B are a little bit more complex. Usually we have like some organic compounds that are covalently linked in order to give, we start from two less complex starting materials, we end up with a more complex intermediate. But that's not the end, usually in our work. We do this on an iteration process. Let's say it's something that we have to do over and over. So there are like 6 or 7 of these chemical transformation in order to get our final product. So if you can see in this picture, in order to get the required API, we start with a relatively simple starting material, and throughout these chemical transformations, we end up having our required active principal ingredient. So in order to obtain this final required compound, we don't have just one reaction. Usually we have to go to several chemical transformations. And I will specify a little bit more what we mean by chemical transformation. For us, chemical transformation is not just simple reaction. Chemical transformation usually has 3 differentiated parts, but at the same time, they're interconnected. There is an interconnection, strong interconnection between them. So the first one is the reaction per se. So we have 2 starting materials that are coupled together or joined together through a covalent bond in order to deliver the desired product and move on. So in this case, we have several parameters that we need to control, that we need to optimize in order to go from a very small scale to a large reactor, as you can see in the picture. And sometimes we even go to reactors that are like 2-story high. So you can imagine that we need an improvement, continuous improvement of the process in this part of the chemical transformation. But we cannot forget about the isolation process. In the reactor, we do have usually a liquid material that we need to end up having a solid material so we are able to handle it. So this isolation process also have a lot of experience and also have a lot of optimization that is necessary in order to get this finally isolated solid material. But this is not the end. We still have another part, which is a purification step. In this purification step, again, the solid material usually is not with the quality that we want, is not the quality that we desire for an intermediate or for a final active principal ingredient. So we need to add an extra step to the chemical transformation in order to make sure that we transform unpure or less pure brown solid material to a completely pure crystalline material. In the purification step, usually crystallization is one of the main operations that's being carried out in order to get that. It is a science by itself, so maybe we can discuss that in another day, but it's an important part of our process as well. So with this, why catalysis for us? What is our interest in catalysis? As you know, in order to get all these transformations from starting materials to intermediates or final products, a lot of the reactions are catalyzed reactions. And here's why we really thank academic people who start from scratch to investigate new catalysis, because catalysis is something which is a breakthrough for our transformations. We know that we have acid, base, metal-based, biocatalysis. So the idea, why is it important for us, is on one side, we can install chirality in a molecule. So that is what is important. All the world around the asymmetric catalysis with its different ways and positions. And why is it important for us? Here is just an example of, probably a lot of you know this example, the thalidomide example, which if you look at the pictures, the molecules look basically the same. The only difference between them is the chirality. But this chirality becomes a key point in order to get either the desired effect or a completely undesired effect. So in this case, for example, the R chiral molecule shown in the left has the desired pharmacological sedative effect, whereas the undesired S chiral isomer shown in the right has a very dramatic adverse effect. And if you know, that has been an issue with teratogenic effects, especially with women, pregnant women, and subsequent chromophore aberrations after being born. So that's one side that we are very interested from a pharmaceutical point of view in order to get drugs that are harmless to the patients. So chirality is an issue. And another important aspect of catalysis for our work, our daily work, is the ability that catalysis gives to access a structurally complex motifs. And this is basically using metal-based catalysis. And as you can see in this example down here, this is an hepatitis C drug developed by Gillette. And you can see here it's just a very complex molecule. But the final step in this synthesis is just the catalysis aid reaction between these two smaller fragments, the blue one and the red one. So just metal-based catalysis aided in this reaction is able to deliver a really complex molecule from much less complex intermediates. Another example, an in-house example that we've had in several projects is this carbon-nitrogen bond formation, where from less complex starting materials as shown here, we can end up having a quite more complex and elaborated intermediate material that we can move forward to a final product. So since when we have used metal-based catalysis in the pharmaceutical industry? Well, this has been a long time ago. For very many years, we've used metal catalysis. And probably you know that the most ancient examples are palladium on carbon to perform catalytic hydrogenation, which is worldwide use, I would say, in all pharmaceutical companies, or palladium acetate for initial cross-coupling reactions and carbon-hydrogen activation reactions. But over the years, new and more sophisticated catalysts have been discovered and have appeared and have had some usefulness in the pharmaceutical industry in order to get more and more complex structures as active pharmaceutical ingredients. So here are some names: Suzuki, Miura, Negishi, Sonoka, Shira, Backwell. You are all familiar with that you are more expert than me in catalysis. So all this is really important for us in order to access structurally more complex, more demanding active principal ingredients. So down below are just some examples of these catalysts. And this outstanding evolution has been mainly achieved with homogeneous catalysts. Why? Well, there are several advantages of using homogeneous catalysts, at least from our perspective, pharmaceutical industry. One of them is its solubility in the reaction media that we perform. With this new and novel catalyst, obviously, one advantage is the improved catalytic activity. So the idea is to use less amount of catalyst compared to older catalysts. So this improved catalytic activity has a direct impact in the process efficiency, let's say in the cost, as well as from a sustainability point of view. So we have a reduced presence of toxic metals in the final products. But the world is not perfect. So there are some things that we have to consider in the pharmaceutical industry before we embark on using some catalysts. You can envision that we have to scale up, use reactions from milligrams to grams, and we have to go to kilograms and hundreds of kilograms in the end. So the catalyst price and availability usually is a key point in an API manufacture. So first of all, we need the bulk manufacture of these catalysts. If it's only accessible from an academic point of view, probably it's not robust enough for us to be used. So generally, the more sophisticated catalysts usually are more expensive. So that has a direct impact in cost that we always have to evaluate from our point of view. So in the end, we need a balance between the improved catalytic activity and the price and availability of the catalyst. So all these three things are in there in order for us to select which is the best way to approach an API. Another important aspect that we take into consideration is the recycling of the catalyst, because the recycling is a very useful way to reduce cost and improve efficiency for us. So one of the drawbacks of the homogeneous catalyst is the difficulty or the tediousness of having of recyclability of them. So you usually need extra steps in your synthetic process in order to get them back and be able to use them. And another thing that is of crucial importance to us is the metal content and metal presence in the end of our active principal ingredient. So as I said before, we are a regulated environment, and we need to have.
Can I just, could you please go to the end of the presentation, because we need to, okay, thank you.
Okay, yeah, so just to show you that several advantages of using heterogeneous catalysts and why we are interested in this hybrid catalyst that we are working on the multi-cat project, which is the easy recycling and the metal leaching, and as a consequence, an improved environmental impact. So here are like some examples that we have that the consortium has prepared in this multi-hat project. Just very quickly to give you a couple of examples on the efficiency of this process, starting from three very simple starting materials, three different alloy groups, we can access way more complex final products. We have here a triaryl system, which is highly substituted. And this is done in only one reaction using the same catalyst for both steps. This is a one-step process. And in the second example, we have a different process where you can see we can access a very elaborated complex carbon skeleton in the end as well. So this is just an example of seeing that we can get very complex structures from simple starting materials by using just one chemical transformation. A good example of process efficiency. And finally, just to give you an example of process efficiency, process sustainability. In this case, we have an example where we've been able to lower down the amount of palladium catalyst all the way down to 0.001 mol% without loss of yield. And more importantly, we have very low metal leaching, very low metal quantity, metal content in our final intermediate. So doing the same conditions with the conventional catalyst used for this reaction, palladium tetrakis, we see that the amount of palladium that we have found in our intermediate is 10 times higher. So with this catalyst that has been tested and synthesized in this project, we have obtained catalyst with outstanding catalyst activity, remarkable low metal leaching, and a very improved isolation procedure. Even at 100 gram scale reaction, just a simple filtration will recover the catalyst, so we can reuse for another reaction. So again, example of process efficiency and process sustainability. If it's okay with you, I will skip the summary because it's just a summary of all the things that I've been talking about, and I will go, because I think it's very important, into the acknowledgements slide, because I think that this work that we have performed couldn't have been realized or obtained without the help of all the partners in this consortium. So thank you all the partners for all the fruitful discussions and all the comments and all the things. So all the successful results couldn't have been possible without you. And just to finish up, thank you for your attention.
Okay, thank you, Pep. So we need to move fast to the last presentation, which will be delivered by Bright Kusema. Dr. Bright Kusema is a scientist, a research scientist in Solvay, where he works in eco-friendly processes. Please, Bright.
Yes, okay. Can you see my screen now?
Yes.
Okay, thank you very much.
But it's a very small screen. We see it very small. You have actually the. Can you make a full screen?
Yes.
Very good. Perfect.
Full screen now?
Perfect.
Okay. Yeah, thank you very much. So I'm going to be fast, try to stay within the time frame. I will give you an overview of our activities for the industrial assessment of catalyst at Solvay, specifically the application of multi-tool high-cut case, which I will go in detail very soon. So my talk is maybe separated into 3 parts. The first part, I will introduce Solvay today, and I will give you an overview of Solvay One Planet goals. And the second part, I introduce the case of multi-tool high-cut, that is single reactor outdoor condensation and hydrogenation reactions, including a brief introduction or overview of some results that we obtained. And finally, I try to make a link between the findings within the project and the connection with our innovation process towards the calculation of full manufacturing cost, for example. So starting off with Solvay, I know most of the people within the consortium are fully aware of Solvay, but I will just go through it to some of the people who are joining for the first time. So Solvay, it is a science company whose technologies bring benefits to many aspects of daily life. And the innovation solutions, they contribute to safer, cleaner, and more sustainable products, which are found in many fields, in homes, food and consumer goods, planes, cars, batteries, smart devices, healthcare applications, water and air purification systems. So the application field is rather broad and very wide. And as a group, of course, we seek to create a sustainable shared value for all, notably through the Solvay One Planet, which is crafted around the three main pillars, involving the protecting of the climate and the preserving of the resources and fostering a better life. I will go through some of the examples within these three pillars shortly. But below, just to highlight some of the key figures within Solvay, and one which I can maybe point out to all of you is that around half or 52% of the net sales, they contribute or are as a result of sustainable solutions. And of course, within Solvay, it's a global company with global presence, not only a geographic presence, but also in terms of the industrial sites and major research and innovation centers within the four major zones of North America, Europe, Latin America, and the Asia Pacific region. And it is suited to better serve our customers in the previous fields, which I highlighted in the slide before. And now going to one of the key parts which I want to highlight and show the link between these Solvay One Planet goals and what we are doing at the moment in the three main pillars, climate, resources, and better life, are the 10 ambitious objectives to reduce our global impact. And the main categories or the main properties is to align greenhouse gas emissions with the Paris Agreement, as well as to phase out the coal as a source of energy and the reduction of pressure on biodiversity. And in the resources is to increase the sustainable solution and increase the circular economy and reduce non-recoverable industrial waste. And the third part is simply to improve the quality of life. I will not go much into detail. But for here, what I want to highlight are the three objectives which are directly linked to the activities of Multi-2 HiCat, specifically in the development of a new catalyst and sustainable processes. And one key example which is worthwhile to mention within Solvay is the satellite peroxide production, where we try to target the elimination of long distance transportation and minimizing the carbon footprint in the production of hydrogen peroxide. And within this My H2O2 project, the energy consumption can be reduced by up to 45% compared with conventional processes. And of course, you know, the key message here is that catalysis and sustainable chemistry, it plays a significant role in achieving these targets. So now going to the Multi-2 HiCat case, it's designed towards the targeting of a single reactor tandem processes. And one of the reaction that we have been working on, Mark, my colleague from CNRS, he already introduced this reaction. It's basically outdoor condensation of furfural with MIBK, followed by the hydrogenation. And the idea was to try to combine the two individual reaction steps using one bifunctional catalyst to avoid isolation of the reaction intermediates and a possible change of solvent. And it is indeed a unique opportunity to develop knowledge on the cost structure and environmental impacts compared to the data for economic and environmental savings generated. And finally, we try to validate the economic and environmental benefits of the new single reactor multifunctional catalyst developed for this process. So here I just give you a snapshot of the microkinetic analysis as well as the parameter estimation after the catalyst screening of different possible candidates. 5% palladium on alumina, it was chosen as the best catalyst for the tandem reaction. And different operating conditions such as molar ratio of full to MIBK, it was determined in temperature, time, and pressure, hydrogen pressure. And the elementary reactions involved in the outdoor condensation highlighted on this scheme, as well as the next step for the hydrogenation. They were derived using the Lingmuir-Hirscher surface reaction mechanism. And the parity plots for Furfrau and MIBK outdoor condensation, as well as the subsequent hydrogenation conducted using palladium on alumina catalyst. It showed a good parameter estimation between the measured values to the predicted values obtained using the model. And this was involving both steps for outdoor condensation as well as hydrogenation. And from these microkinetic analysis, the best experimental conditions, they were obtained, and they were subsequently used for further cost estimation assessment, which I will show in the next slide. And the key point is to try to make a link between the new findings obtained using the developed a new catalytic system and make a link or a connection with the innovation process within Solvay, which tries to focus or highlight the sustainability within the Solvay FACEGAT project management. So basically we try to use different tools for piloting innovation towards sustainability at each step along the innovation process. And starting from idea generation to opportunities where we develop the ideas to a proof of concept. And we believe multi-tool HiCAT, it started this phase. And when it successfully goes to a fully, I would say, mature industrial project, this is the part when it is developed from a proof of concept to value generation for Solvay. And all these steps, of course, they are market driven towards the target application. And in doing so, we also make use of CVAL. This is a monitoring cost to guide strategy, one of the tools that we apply for all our different innovation projects within Solvay. And the CVAL, it's basically see the value of a project, calculating both its economical and environmental impact. And the starting point or the basis, of course, is to generate a block flow diagram using the data which is generated at the initial stages of the project into a fully, I would say, functional, or you can call it a functional process, taking into account calculation of mass and energy balance, as well as the price and impact from the databases that we have. And the next step is to validate or compare the economic assessment, that is the manufacturing cost of the desired product, as well as taking into account the environmental assessment, whether you need to do further purification of the final product, as well as a recycling of unreacted raw materials, as well as the treatment of waste generated in your process. And these elements are then treated in a CVAL basically combining the economical and the environmental impact of the elements of the project and monetizing them to obtain we call it a variable cost, where we see what is the true value of the product. And the last part, of course, is to make a complete full manufacturing cost. And the full manufacturing cost, it already takes into account the process scheme when we assume or make assumptions what could be the maximum productivity of the process towards a desired product, as well as mass and energy balance and capital investments which are needed or required in the project, and the raw material and the catalyst prices. And all these elements, of course, they will finally give you the full manufacturing cost. And for the multi-tool high-cut case study, the full manufacturing cost, it was obtained or determined to be 3.9 euros per kilogram. And within this price, up to 64% of the full manufacturing cost is composed of variable cost. Basically, this is the price of the raw materials and catalysts which are involved in the process, and the energy costs. And we believe that from this full manufacturing value, up to 20% of the costs can be improved simply by improving your catalyst or the process conditions in the multi-tool high-cut case. So just to sum up my talk or my presentation, I have tried to highlight the multi-tool high-cut case for single reactor strategy for aldehyde condensation and hydrogenation reactions. And indeed, it was a methodology to assess the impact of catalyst in eco and environmental aspects. And the microkinetic analysis, it was conducted in the best experimental conditions at lab scale, were used as a basis for further cost estimation and environmental aspects. And therefore, the multi-tool high-cut case of aldehyde condensation and hydrogenation, the full manufacturing cost, it was evaluated at 3,980 euros per ton under the conditions of a one-step or cascade strategy. And the main levers for economical and environmental cost reduction, mainly within the prices of the raw materials or the ratio of the reagents, and the potential cost savings can be increased up to as much as 20%. And the one-pot reactor strategy, it offers good prospects with a potential gain of up to 20% of costs compared to the multi-stage scenario. So overall, although the lab scale conditions are far from scale-up or pre-industrial conditions, the multi-tool high-cut case, it offers positive trends in favor of using a new bifunctional palladium monoaluminum catalyst and the development of multi-site organic-inorganic hybrid catalytic processes. And with this, I acknowledge all the colleagues within Solvay who participated in the multi-tool high-cut project, as well as all the external partners. And I thank you all for your kind attention.
Okay, thank you, Bright. I really appreciate your presentation, your clear presentation, especially the vision of the Solvay. And all of you know it's a very large company, multinational company. So, and especially how the multi-tool high-cut was in the strategy of the your company. So thank you, Bright. Now, just to conclude, I would like to thank all of the speakers, starting from the two plenary lectures, let's say the keynote lectures, Silvia Bordiga and Hermenegildo Garcia. Just a moment. Okay. And of course, all the speakers, that they deliver some general aspect of hybrid materials, hybrid catalysts for enhancing relevant industrial processes. And I like really to thank all of these speakers because they spent some extra time to do this besides after the final meeting of yesterday. So thank you very much, Urbano, Mark, Robert, and all the other speakers. And I hope, really hope, to see you soon, to meet in presence and to exchange ideas and couple beers as well. Thank you very much. And of course, all the people connected to, that are connected through the website, the department website, through the YouTube. So thank you very much for assisting, for to be present to the end. So okay, again, have a good time, have a good lunch. Bye. See you soon.
Thank you.